Okay, so let's jump into virtual memory. We may talk about that more tomorrow, but we're going to talk about virtual memory. Here, I didn't add many readings over here, as you can see, except this is covered somewhat. Well, it's covered actually in not a bad way in H&H. I'm going to borrow some slides, so you can actually find some reading in your book because it's such a fundamental concept. Even though books ignore some of the fundamental concepts like prefetching, they don't ignore virtual memory, as you can see. Okay, so the programmer's view of memory looks like this, essentially, right? Memory looks like something for you, and if you didn't take this course, memory would always look like this for you, basically. It's just some magic underneath. In fact, if you don't take any course that shows how a processor works, it's all magic, right? I cannot imagine a word like that, right? You write this program and some magic executes it, and you're not curious about that magic underneath. That's the reason why you have this course in a computer science degree, right? We're going to become a computer scientist or a computer engineer. Hopefully this should not be magic to someone who claims to be a computer scientist, right? Maybe there should be better degrees or some other degree for people who want to keep it as magic, right? So that's the whole point of understanding how a computer works. So this is not magic, as you know, but from the programmer's perspective, we do loads and stores to memory, right? So we know that ideal memory underneath is not magic. Ideally, we want this magic also. We want zero access time, infinite capacity, zero cost, infinite bandwidth, zero energy, ... Today, we're going to tackle the infinite capacity problem a little bit. But we're also going to introduce other stuff because virtual memory is actually serving multiple purposes in today's systems. One is hiding the management of memory, hiding the capacity issues with memory from the programmer. And the other is protection, access protection, isolation, right? These are two completely different problems that are actually solved in an integrated manner in the virtual memory system. Okay, so remember the slide. We said we have virtual memory and programmer sees virtual memory, and this is an abstraction actually, because underneath there is some physical memory. And programmer can assume the memory is infinite, large enough. In reality, physical memory size is much smaller than what the programmer assumes. And things work. You write programs with large virtual addresses. In reality, that large of an address doesn't exist. You have a 64-bit address. We don't have 2 to the 64-byte memories, right? If you have that, please let me know. I'd like to use it. So basically, physical memory size is much smaller than what the programmer assumes. And underneath, there's some magic. The system, using some magic, meaning using software and hardware cooperatively, maps virtual addresses to physical addresses, virtual memory addresses to physical memory. And we're going to uncover that magic today. The system automatically manages the physical memory space transparently to the programmer. And this is another reason why this was a very successful idea. If you actually had to find system ideas that have been extremely successful, virtual memory is one of them. But hopefully we'll also say that this may not be the best way to go forward by doing critical thinking either later today or tomorrow. Okay, but it's been very useful. So programmer, essentially the big benefit is programmer does not need to know the physical size of the memory, nor do they need to manage it. A small physical memory can appear as a huge one to the programmer, and essentially life is easier for the programmer, right? And we're going to actually add more and more over here. This is a simplification because there are other benefits of virtual memory, as we will see. But of course, the downside is somebody needs to pay the cost of actually making this work, and that's the system software and architecture, essentially, microarchitect and the system designer. And this is a classic example of the programmer microarchitect trade-off, right? You make programmers' life easy by making microarchitects' life hard. Precise exception is another example, right? We retire instructions in order, and we have to pay the cost of doing so. So this virtual memory requires indirection and mapping between virtual and physical address spaces. And this will become more clear because you need to, programmer sees a virtual address space and then there's a physical address space, and there needs to be some translation that needs to happen from the virtual space to the physical space and mapping that happens, because not the entire virtual memory that the programmer sees is going to be in the physical space. Okay, so let's talk about benefits of this automatic management of memory. Basically, we're talking about automatic management of memory. Programmer doesn't need to deal with physical addresses, and this has a lot of benefits, actually. Each process has its own virtual address space, which is very large. Basically, for practical purposes, infinite. You can run out of virtual memory space also, but maybe you're not doing something right if you're running out of virtual memory space in your memory management. Maybe you have a memory leak somewhere, right? possible. Each process is an independent mapping of virtual to physical addresses. Basically, this is very important to know. Each process or each program has a different view of virtual memory. Independent, completely independent. They may share parts of the physical memory through the mapping, their own mappings, but they are independent on the virtual memory address space. On the other hand, threads within a process share the virtual memory space. That's the difference between process and thread, right? Which you will also see, I think, when you take systems programming. So virtual memory or this automatic management of memory enables multiple things. It enables code and data to be located anywhere in physical memory because you have this indirection, right? This will become a little bit more clear. Basically, you can have relocation and flexible location of data and code. If the programmer directly encoded a physical address, and that physical address, basically, the code has to be there, right? Whereas if it was a virtual address and there's a translation mechanism afterwards, the system can load the program into any location in physical memory by just changing the translation, right? This gives a lot of flexibility to the system. I mean, hopefully it's obvious, but you will see more. This also enables isolation or separation of code and data from different processes in physical memory. So if somebody writes a program X and you write program Y, these can be isolated from each other because the system has actually different mappings, virtual to physical mappings. This is called protection and isolation, and we will see that essentially. So I should also mention that this is important because this is what enables multi-programming. Multiple programs can be present in the same machine. Otherwise, they're very, if you don't have some sort of translation or indirection, it's very difficult to enable because I write a program and I want it to be executed and I assume some physical addresses. Somebody else writes a program, they assume some physical addresses. What if those physical addresses overlap? How are these two things going to execute if there was no translation mechanism, right? It's not going to happen clearly because they will, I do a write to a physical address A, somebody else does a write to a physical address A. Clearly, these are different programs. They should not be writing to the same location because that address A means something else for each of the programs, right? These are semantically completely independent. But if you don't have a mechanism of remapping those addresses somewhere else, meaning if the programmer directly gets exposed to the physical address on the machine, you will have that problem. You cannot execute multiple processes at the same time. Okay, and then the other benefit of this is code and data sharing between multiple processes also happen through virtual memory. So you may, again, I write program X, somebody else writes program Y, and we want to share data somehow with each other. What do? I call my friend and say, oh, I'm writing this data value to physical memory location A. So you'd better read from physical location A. That's what you do today, right? No, you don't do that today, right? So basically, you use some shared memory constructs today, or shared libraries, right? If you have shared libraries in a machine, how the different programs can call functions that are shared. Okay, these will become more clear, but essentially these are enabled by automatic management of memory. So a system with physical memory only essentially CPU generates physical addresses, and this is really the physical memory. Load or store instructions generate physical memory addresses. Early computers were like this. Today, this is not the case. Although you could make x86, for example, work in physical mode. It's called real mode in x86. So if you want, you can actually make this work. So this sort of thing is visible to the BIOS, for example, the system, a very low-level system software that enables a big startup of your machine, because you have to access physical memory directly so that you can load some things like page tables, as we will see. But today, most programmers do not directly manipulate physical addresses. Okay, so basically, in a system that looks like this, let's assume that this is the baseline, physical memory is of limited size because of cost reasons. We've seen that. Right? What if you need more? Should the programmer be concerned about the size of the code and data blocks fitting physical memory? Right? You write some code, your code is larger than the physical memory. What do? Do you actually do the hard work to manage the data moment from disk to physical memory? Well, if you start doing that, it becomes very difficult to program this machine. So we're going to tackle this problem with virtual memory. Multiple programs may need the physical memory. Should the programmer make sure all processes, different programs, can fit in physical memory? We just said that it's not possible because different people may be writing different programs. And even if the same person is writing, it's a mess to actually think about this, right? Should the programmer ensure that two processes do not unintentionally or incorrectly use the same physical memory portion? This was the example that I gave you earlier, writing to location A by two different programs. And then there's another problem, which is actually interesting because your instruction set architecture may be forward-looking. They may have an address space greater than the physical memory size, right? Today we have 64-bit addresses, right? 64-bit address space with byte addressability is 16 exabytes. How many of you have 16 exabyte memory? Not even supercomputers have 16 exabyte memory today, unfortunately. So clearly we have an address space that's much larger today. So how do you actually deal with that, right? I mean, this is actually interesting because this is actually, the address space is virtual. That's why it's 64 bits, but keep with the problem for now. Okay, so basically, what if you do not have enough physical memory? Then you still need to have this mapping mechanism that we're going to talk about. So the difficulties of direct physical addressing is a lot. Essentially, the programmer needs to manage the physical memory space. This is inconvenient and difficult, clearly. It used to be this way. People used to manage their physical memory actually in the 1950s, 60s. Good that you're not in those times, let's say. It's more difficult when you have multiple processes. It's difficult to support code and data relocation because addresses are directly specified in the program, right? You cannot relocate the data easily, or you cannot relocate the data essentially if you don't have some indirection or change of address. It's difficult to support multiple processes, especially concurrently, because you need protection and isolation between multiple different processes. And sharing of physical memory space without problems becomes not easy to handle. And finally, difficult to support actual data and code sharing across processes because different processes need to reference the same physical address. And we talked about that also, right? How do you actually communicate that you are supposed to reference this particular address? So essentially, virtual memory solves all of these problems with a single idea, let's say. And the idea is very simple. Give each program the illusion of a large address space while having a small physical memory. Okay, so that's a very high-level idea, clearly. The question is, how do you do that? We're going to talk about that. But the programmer does not worry about managing physical memory within a process or across processes, essentially. Programmer can assume they have infinite amount of physical memory. Hardware and the software cooperatively and automatically manage the physical memory to provide the illusion that we want. And illusions maintained for each independent process. I have to emphasize this. Virtual memory is not a system level thing, it's a process level thing. Each process is its own virtual memory. Okay, so let's talk about the basic mechanism. Basic mechanism is very simple, indirection and mapping of addresses. Essentially, address generated by each instruction in a program is a virtual address. It's not directly specifying anything, any physical entity, basically. It's a virtual address. It could be, you can think of it as a name, right? It's a namespace. It's a virtual namespace. Basically, it's definitely not the physical address used to address main memory. It's going to be translated to the physical address that's going to be used to access main memory. This is also called a linear address in x86. x86 has interesting terms. This is where I don't think they did a good job in terminology, let's say. And then there's an address translation mechanism maps this address to a physical address. And we're going to talk about that address translation mechanism. That physical address is called real address in x86, which is not bad actually in terms of terminology, let's say. And the address translation mechanism can be implemented in hardware and software together. I'm giving you the x86 equivalents because I'm going to show you some examples from x86 here. Okay, so let me give you the conceptual view. This is from the book chapter that I assigned to you. I like this high-level view. Essentially, you have illusion of large, separate address space per process. This is essentially summarizing what the mapping and indirection looks like. In this case, you have two processes. They have independent virtual address spaces. And you can see that each of them have a view of virtual memory that's 256 terabytes. That's 2 to the 48, right? Bytes, essentially 48-bit byte addressable address. The other process also has a virtual address space. But then there's a physical address space. This is actual physical memory. And this system, this processor may have 8 gigabytes of physical memory, right? So essentially, the programs have the illusion that they are operating on 256 terabyte address space each, but individual portions of or chunks of the virtual address space get mapped to physical memory at a given point in time. So essentially, the physical virtual address space is divided into virtual pages. We're going to talk more about that. In this case, 4 kilobyte virtual cases. That's an example. It could be 1 megabyte, 1 gigabyte. We will see. But 4 kilobyte portions of the virtual address space actually get mapped to the physical address space, and they're present in the physical memory at that point in time. So there needs to be a table that records this mapping clearly, right? What is for this process, for process 1, where does virtual page 0 in this particular case get mapped to, right? Does it get mapped to physical page 0? No. It gets mapped to physical page, whatever, but it's actually 0, 1, 2 in this case, right? As you can see. On the other hand, the virtual page 0 of this process gets mapped to physical page 0. So somebody needs to manage this clearly, okay? So that's what the indirection mapping means. You have a virtual address in your program. By some indirection mechanism, you indirectly access physical address space, and that indirection is enabled by mapping of the virtual page number to the physical page number through some lookup table that we will call the page table, okay? So let's take a look at that page table. Essentially, we need to translate the address. Essentially, let me go back here. As opposed to this picture, oh, wow, it was so far away. Even more. Okay, as opposed to this picture where you're directly generating physical addresses, we have an indirection. Okay, essentially, the indirection is this page table, right? The CPU program generates virtual addresses, and you consult this lookup table called page table, and the page table basically says, oh, this virtual page for this process is in this physical page in physical memory. And if you access something that's not in physical memory, it says, oh, it's in disk somewhere. So I'm going to call the system. I'm going to ask for help. This is called an exception. Remember the exceptions and interrupt sector? This is called a page fault exception. The page that the program is referencing is not in physical memory. So I'm going to ask the operating system to help me bring it to the physical memory. And we're going to talk about how that's done. The I/O controller needs to get into the process and handle the exception. Essentially, a page needs to be moved from the disk to the physical memory. And then the mapping needs to be fixed such that that page, the page table entry of that page points to the physical memory page where the page is put into from the disk. Makes sense, right? So this is all done automatically. If it was not done automatically, the programmer had to do all of this. And there was a time in the world 50, 60 years ago when that was the case, okay? In some systems actually, but in maybe 20 and 10 years ago, right? In some cases, maybe it still exists, but very small amount. So basically the hardware converts virtual addresses into physical addresses via this lookup table, page table. But this page table is actually cooperatively managed by the operating system and the hardware together. So we're going to talk about this management. But this makes sense, right? You have virtual memory address space. Some pages in that virtual memory address space is in the physical memory. These are these indirections or these mappings. Some pages, because they have not been accessed recently, for example, are actually on the disk. But you have a mechanism to bring it from the disk to the physical memory. This is why disk is a backing store of virtual memory, of physical memory. And this is why physical memory is a cache of the disk from this perspective, right? From the program's perspective. So essentially, all of the caching principles apply to physical memory as well, as we will see. In fact, I'm going to show you a slide where caching terminology and virtual memory terminology are going to be very similar. Okay, so let's take a look at these two different processes. Each process has 4 GB over here. I'll go through this relatively quickly. Basically, sizes don't matter in this case. This is a small system, as you can see. Physical memory is small. We divide the virtual memory of each process to virtual pages and divide the physical memory into physical pages. I will also call physical frames. You may actually see both, but we'll use physical page in general. And then there's a mapping of the virtual pages of process 1 to the physical pages in physical memory, and ditto for process 2. And that mapping is done through the page table. Clearly, there are many issues in this injection and mapping, right? When to map a virtual address to a physical address. Let's answer that actually quickly. Essentially, when the virtual address is first referenced by the program, nothing has to be in physical memory. Well, the code hopefully is that you're executing, but even the code, right? You have a program counter. The program counter is virtual address. You go through this translation mechanism and get a page fault, and the code gets brought from the disk into the physical memory after that page fault. And then you can reference that program counter in physical memory, right? So basically, whenever you touch a virtual address the first time, that virtual address gets mapped to a physical address through the page table. Of course, you can do prefetching on this as well, right? So you can actually pre-populate this page table both from the operating system perspective and hardware perspective. So what is the mapping granularity? This is important. I showed you 4 kilobyte, for example, right? But it could be byte granularity. It could be kilobyte. It could be megabyte. It could be gigabyte. We have multiple granularities. Existing systems actually have multiple granularities with some pain. This is not an easy task, let's say. But this granularity determines the size of the tag store, which is a page table. Page table is actually a big tag store if you think about it, right? Because physical memory is a cache for the disk. Essentially, if you have byte granularity, that mapping is very small, right? And you don't want that because the tag store is huge. And also, you're not exploiting locality very well if you have pages that are of sizes of bytes. If it's 4 kilobytes, not bad. 16 kilobytes, 64 kilobytes, they exist. Megabytes, gigabytes, now we're going to talk about these. Basically, similar issues like caching over here, right? This is, you can think of it as a cache block size, similar to page size. So where do you store and how do you store the virtual to physical mappings? We're going to concern ourselves with this a little bit. Basically, this has to be an operating system visible data structure. Do you also cache it in hardware? We're going to see the answer is yes. Do you manage it cooperatively? And we're going to see the answer is yes. So this is actually a very great example of hardware-software cooperation also. All of the systems actually do this today. So when do you do, what do you do when the physical address space is full, when your physical memory is full? Well, remember, physical memory is a cache, right? Essentially evict an unlikely to be needed virtual page from physical memory and fix the mappings in the page table. That's the idea, because page table is a tag store, right? Okay, so basically, if you think about physical memory as a cache and the backing store as the next level, and the page table as a tag store, all of this becomes easy, in my opinion, because we've already seen caches. Okay, so virtual, let's go into a little bit more detail. Virtual address space is divided into pages. Physical address space is divided into frames, just to be a little bit different, because it's actually a physical location, frame of a page, if you will. But people call it pages also. That's why I have this IE pages for now. But let's stay with the frame terminology for some time. A virtual page is mapped to a physical frame if the page is in physical memory, okay? That's what the mapping specifies in the page table for that virtual page. Otherwise, the virtual page is mapped to a location in disk, assuming it's allocated. There's also the memory allocation part that we're not going to discuss as much. I'm going to assume all of memory is allocated, but actually when you program, you allocate some memory, and that allocation enables you to have a mapping to the disk or physical memory. But for now, ignore that allocation, let's say. Otherwise, it will complicate things, but there's another level of allocation over here, which is different from what we're talking about here. Assume all of the memory is allocated, all of the virtual address space is allocated, then a virtual page is mapped to a location in disk or a physical frame. If you access a virtual page and it's not in memory, but it's on disk, virtual memory system brings the page into a physical frame and adjusts the mapping. This is called demand paging. And the fact that you found the virtual page not in memory is called a page fault, and we're going to see that. And page table is a table that stores the mapping of virtual pages to physical frames. And you've seen an example, we're going to see more. So in other words, basically physical memory is a cache of the cache for pages that are stored on disk. In fact, it's a fully associative cache in modern systems. A virtual page can be mapped to any physical frame, okay? Similar caching issues exist as we have covered earlier. Placement, replacement, granularity of management, write policy. And we're going to see some of these again, but we're not going to talk about a lot of these. So for example, where and how to place and find a page in cache. What page do you remove to make room in the cache, meaning physical memory? Do you have large, small, or uniform size pages? What do we do about writes? When you write to a physical page, do you also write to a copy on disk? And people quickly figured out that it's a very bad idea to have write through physical memories. So today, our physical memories are write back, meaning you have a modified bit in the page table. This is the same as the dirty bit or modified bit that we've seen in the caches. For a given virtual page, you have a modified bit. If the program has written to that page, that modified bit is set. And when you have to evict that page from physical memory to make room for some other page coming from the disk, you have to write back that page that is marked dirty into the disk. Makes sense, right? But this is not news for you because we've already covered caching. We just changed where the cache is, essentially. Okay, so this is essentially analog. A cache block is analogous to virtual memory page. Cache block size analogous to page size. Block offset is a page offset. A cache miss is essentially a page fault in this case. The index into the cache is the virtual page number in this case. The tag store, metadata store, is the page table, and the data store is actually the physical memory. Physical memory is your data store right now. Okay, I like the slide, as you can see. It simplifies a lot of the concepts. But let's go into virtual memory a little bit more. So page size is the mapping granularity of virtual to physical address spaces. It also dictates the amount of data transferred from hard disk to DRAM at once. And the reason a lot of the page sizes today are 4 kilobytes are historical, because the disks were designed that way. They could bring, let's say, 512 bytes, 4 kilobytes easily through streaming. We actually still have this legacy of disk-based virtual memory systems. That's why you see 4 kilobyte pages today in many systems. It's unfortunate, but that's how it is. Basically, we're assuming that you're transferring all of that amount, 4 kilobytes, from the hard disk to DRAM to put a page into the physical memory. Hopefully that makes sense. But again, we've seen in caching, sub-blocking or sectoring, right? You could actually play similar tricks in virtual memory. Of course, you need to be a little bit more careful, because now you need to change the page table. Because remember, sub-blocking or sectoring enabled us to bring only a piece of the cache block into the cache. You could do that in physical memory as well, but it requires you to actually have the valid and dirty bits separately for different sub-pages in this particular case. Okay, page table is the table that stores virtual to physical page mappings. It's essentially a lookup table. Basically, it's used to translate virtual page addresses to physical frame addresses and find where the associated data is, essentially. An address translation is the process of determining the physical address from the virtual address. So hopefully these are clear. Now let's take a look at how this is done. I've already shown you this picture. Now we're going to actually see some examples. Essentially, this picture is from your book. You can see the chapter. The hope is that most accesses hit in physical memory. So essentially, these are your virtual addresses. There's an address translation mechanism. Some of your virtual addresses in physical memory. Some of them are in hard drive or SSD, essentially disk. The hope is that most access hit in physical memory, but programs see the large capacity of virtual memory such that the programmer doesn't need to worry about the sizes of data or code. This is essentially the idea of a memory hierarchy also, right? If you think about it, this is what we said, right? Most accesses we want, it should hit in the fast memory, and we should get the capacity of the large memory, right? That's the idea. So you can think of this as, this is the cache and this is the large memory over here. Okay, so this is what address translation looks like. You take a virtual address, in this case it's 32 bits. You chop off the bottom bits like page offset, because that's the page size. Those bottom bits don't change during the translation. But the top part, the page number, virtual page number, gets translated to a physical page number or physical frame number. Let's call it physical frame page number. That's what your book uses. Makes sense, right? By just looking at this, now you can tell what's the size of your physical memory, right? It has 27 bits, so it's 2 to the 27 bytes, assuming it's byte addressable. And your virtual address is 32 bits, is 2 to the 32 bytes. Makes sense. So this translation mechanism we're going to look at. So essentially, a 19-bit virtual page number gets translated to a 15-bit physical frame number. Everything is good, right? So let's take a look at the example. Actually, this was 31, sorry. Yeah. Virtual memory size is 3 gigabytes in this example. So you have 3 to 31 bytes. Physical memory size 2 to the 27. Page size is 2 to the 12, 4 kilobytes. Essentially, the organization looks like this. Virtual address is 31 bits, physical address is 27 bits, page offset is 12 bits. So the number of virtual pages you have is 2 to the 19, number of physical pages 2 to the 15. So you can actually easily drive the virtual page number and physical page number. These are easy. And this is an example from your book also. This is what your virtual memory looks like. This is what your physical memory looks like. The blue items over here, or the blue pages, actually are present in physical memory. And we're looking at the granularity of virtual pages and physical pages, as you can see, right? This, for example, shows that virtual page 2 is mapped to physical page 7 FFF. And clearly, physical memory is smaller. Okay, so essentially, how do we translate addresses? Page table has entry for each virtual page. So for every possible virtual page number, you need to have an entry. And each page table entry has a valid bit. This valid bit says if the virtual page is located in physical memory. Basically, if it's 1, the virtual page is actually located in physical memory. Otherwise, it's somewhere else. So you need to have a mechanism for finding where it is. This stuff can be stored in the page table or some other data structures in the operating system, which we're not going to get into. But it must be fetched from the hard disk somehow. I should actually call it a backing store because it can be something else. Right? It could be tape. It could be some SSD. Physical page number is where the virtual page is located in physical memory, assuming valid bit is 1, right? And then there are also some other bits in the page table entry, like dirty, modified, we talked about, replacement policy bits. What are you going to replace? How similar to the cache replacement, basically. We're going to look at that also. And then also permission and access bits. Can you access this page, given that you have some privilege level in this process? We're going to talk about that because this is separate from address translation. Essentially, it enables virtual memory protection. Okay, so ignore those permission access bits for now. So let's take a look at this example page table for the example in your book. Essentially, you have virtual page numbers, and this is your page table, ignoring the access protection and other replacement policy bits. You have a valid bit that's set for only those virtual pages that are in physical memory, and it shows the mapping, as you can see, right? So in this case, you see 1, 2, 3, 4 of the virtual pages present in physical memory. Okay, let's take a look at the address translation, how it's done. Basically, you take the virtual address, 31 bits, chop off the page offset, because this doesn't change during translation, because that's the page size. You find the virtual page number. You use the virtual page number to index into the page table. Remember, page table is also something in memory. So now you need to think a little bit. Basically, you need to index into the page table to get the page table entry. And that page table entry specifies the valid bit and the physical page number. Right? So basically, page table is located at physical memory address specified by the page table base register. Now here, you need to think a little bit, because in order to access memory at a virtual address, you need to access memory to get to the page table entry first. This is the indirection, right? This is why the load indirect is a nice instruction in LC3, for example, right? But basically, we're assuming that the page table is an entire memory. We're going to deconstruct that soon, because how are we going to have this huge thing in physical memory, right? But basically, there's a page table base register. It's a physical address. You add to it the virtual address times the page table entry size, and that gives you the address of the page table entry that you're looking for to do the translation, okay? Basically, page table is indexed with the VPN, virtual page number. The page table provides the PPN, which is the physical page number, which is, in this case, 0x7FFF, and it's valid. So the translation is basically concatenating the page offsets with the physical page number. Right? So page offset bits don't change during translation, as expected. Makes sense, right? Okay, so we're going to look at a bunch of issues over here, but let's go through a relatively simple example. What is the physical address or virtual address 5F20? We first need to find the page table entry containing the translation for the corresponding virtual page number. So what is the virtual page number? You need to figure that out. We're going to figure that out soon. And then we look up the page table entry at the address, meaning do a memory access there. And what is the memory access that you need to do? Essentially, there's a page table base register. We add to it the virtual page number times the page table entry size, because each page table entry occupies some amount of space, right? So let's do this for the question that I asked earlier. 5F20, if you look at it as a 31-bit entity, you'll figure out that page offset is F20 and virtual page number is 5. So VPN is 5, meaning entry 5 in page table indicates VPN 5 is in physical page 1. Well, we basically look up the page table in entry 5. This is entry 0, 1, 2, 3, 4, 5. It's valid, meaning it's in physical memory, and the physical page number is this. And we do the translation, so the physical address is 1F20. Makes sense. And then the question is, another question, what is the physical address of virtual address 73E0? We do the same thing. VPN happens to be 7 over here, because the bottom 12 bits are the page offset. We look at the entry 7 in the page table, valid bit is 0, which means that this virtual page is not in physical memory. That means that whatever I see over here is not useful for me for translation, but it may be useful for figuring out where this is. So this is a page fault exception. At this point, exception handling happens. Remember precise exceptions lecture when we talked about exception handling? This process, you save the architectural state, and then you basically give an exception code, and an exception handler is called. This exception handler comes in, it checks what's going on. It says, oh, this is a page fault exception, so I better service this page fault. So you jump to a page fault exception handler that services that page fault. We're going to see that soon. Okay, so let's take a look at some of the issues over here. So page table size, we should tackle this because this is going to be hairy if you don't tackle it. So let's take a look at a bigger virtual memory address space like we have today, 64 bits, right? So if you look at this, assuming 4 kilobyte pages, page offset is 12 bits, virtual page number is 52 bits. Assume that your physical address space is 40 bits. Your page table is responsible for translating 52-bit virtual page numbers to 28-bit physical frame numbers or physical page numbers. Sounds good. Okay, I can deal with it. But how large is this page table, really? Well, 52 bits means 2 to the 52 entries, right? First of all, that's to begin with, it is a large number. Assume conservatively that it's only 4 bytes per entry. In existing page tables, actually, it's larger. So this is 2 to the 54 bytes. That's 16 petabytes, right? Do you have it in your physical memory? I wish I had it. I wouldn't use it on page tables if I had it. Let me put it that way. Basically, and that's just for one process. Never forget that. If you're running 100 processes, multiply this by 100. If you want 1,000 processes, multiply it by 1,000, right? Basically, this is not realistic. And the process may not be using the entire virtual memory space. Allocated, not allocated comes into play, but I'm not going to talk about that over here. Basically, this is not realistic today. So a page table is large. It's actually huge. But at least part of it has to be located in physical memory. We said that page registers in physical memory, right? So how do we get rid of locating entire page table in physical memory? Clearly, we're not going to be able to do that. So solution is more indirection. Essentially, multi-level or hierarchical page tables. In other words, this is more indirection. We'll see that we'll do more indirection. We're not going to get to the page table entry immediately. We're going to go to another level of page table that gives us the page table entry. Okay, so multi-level page tables. Basically organize the page table in a hierarchical manner such that only a small first level page table has to be in physical memory. And that small first level page table hopefully is 4 kilobytes or 8 kilobytes, right? So that's the idea. Essentially, this is from your book. This is what it looks like. You have, you chop the address into 3 things. The top part specifies which page table to look up. So this is called the page table number. And then there's an offset inside that page table. So essentially, this is the first level page table. You can see that it's 9 bits, right? So you index using this first level page table. This gives you the base register of the page table that you actually need to index. Makes sense, right? In a 2 level, after one access to the first level, you get the base register of the page table you actually need to index that houses your page table entry that you're looking for the translation in, right? So, okay, let's take a look. Page table number, you index here. Of course, this needs to be in physical memory now, but this is small. This is 2 to the 9 times 4 bytes, let's say, or 8 bytes, whatever, right? Basically, it's smaller than 4 kilobytes or equal to 4 kilobytes. So it fits in your page also nicely, right? So the entire virtual memory system is designed based on this principle. The first level fits in your physical page, and it stays in physical memory so that you don't get a page fault on your page table, right? First level page table. But on the other level page tables, you can actually get a page fault, which is actually interesting. Okay, so let's not get ahead of ourselves. Essentially, this is the page table address, and that gives you which page table you're going to index. And this is your index into that page table. So each of these page table is 1K entries, as you can see, but you have many of these page tables. You can calculate how many you have. I'm not going to do that right now. So first level page table must be in physical memory. Only the needed second level page tables can be kept in physical memory. So if you haven't touched that memory, you don't need to bring the page tables that do the translation for that virtual memory address space. So this is another beauty of multi-level page tables. It solves the problem of not having or problem of having having your physical memory covered with the page table, right? Only the page tables that you have touched are brought into the physical memory. Okay, so this is an example, as you can see. This is the address that we have. This is the page table number, and this is 0. Essentially, we're accessing, we want to find the page table address for page table number 0 over here, the top 9 bits. and that's the page table base register, which happens to be in physical memory in this particular case, right? Essentially, essentially it is in physical memory, sorry, it's valid, as you can see over here, and then you can access it, yes. And then the translation is also there. Basically, the page itself is in physical memory. So here, the top level page table, the page table that you're looking for is in physical memory, and then the page you're looking for is also in physical memory. But if you actually access page table number 01, you can see that it's not in physical memory, right? The page table that you're looking for is not in physical memory, so that's a page fault for the page table you're looking for. So the virtual memory system needs to bring the page table you're looking for into the physical memory and fix the mapping over here. Okay? I know there's a lot of injection going on, but you'll get used to it. So basically, we solved some problems with more indirection, but this cost us something. For n-level page table, now we need n page table accesses to find the page table entry, assuming all of those page tables that we're looking for are in physical memory. So n accesses, we were just doing one additional access, now we want n accesses. This is going to increase our latency to actually get the translation. So let me give you an example from x86 architecture. You can see that x86 nicely called this page directory. So CR3 is the physical address. So basically control register 3, or this is the page directory base register. You add to it the top n bits from the directory entry, and then this gives you the base register of the actual page table. And then you index that page table using the part of the linear address. That gives you the PTE, and then PTE concatenated with the offset is the physical address, essentially. So with small pages, that's what it looks like. This is 10, this is 10, as you can see, 10 bits, 10 bits. And you can see everything fits nicely in 4 kilobyte pages if you do that. But x86 actually has large pages also. This is a 4 megabyte page. Large pages are single level, as you can see, right? So you have a single level page table. x86 also has large addresses. This is 48-bit address, and they have 4-level paging. Because I don't remember what PML4E means, I had to write it, page map level 4 entry over here. Basically, you take the page table base register, index into it using this top 9 bits. That gives you an address that will start the next page table and index into it using the next 9 bits. And then that gives you another address that will start with the page directory. That's the start of the page directory. You index into it using these 9 bits. And finally, you get your page table base register from there and index into it using this address 9 bits over here. And you get the page table entry, hopefully. And assuming these are all valid, 1, 1, 1, 1, 1, you'll get the physical address after 4 translations. But you can also get 4 page faults over here, right? So basically, your latency can be very high if you get 4 page faults. Okay, I think this is a great place to stop because we're going to move to the next challenge. And next challenge is going to introduce more caching, let's say. So we'll pick up here tomorrow and finish up virtual memory and talk about. So let's continue virtual memory and finish. Virtual memory never ends, so it's impossible to finish virtual memory, in my opinion. But we'll finish at least the basics and interesting parts. There's a lot more that's interesting. This is an idea that's been around for 60 years. And in the end, we'll spend a little bit of time to critically question it because it's probably not the best way of managing memory going into the future as memories become larger. You have different types of accelerators sharing the memory, etc. So, and you will see some of the reasons, hopefully, toward this lecture, within this lecture. Okay, you know there's an extra assignment to get easy credit on. We're going to talk about that hopefully toward the end of this lecture. And you have some readings, which have not changed that much recently. And recall virtual memory is really providing the illusion of a large separate address space per process. And this is a nice picture that I like using. Essentially, each process has its own virtual address space, which is large. And then physical memory is small. And you have this indirection and mapping mechanisms that map the virtual address space of each process to portions of the physical address space. And there's a management system that ensures that the programmer doesn't need to deal with managing the address space, virtual address space, managing the physical memory in any of the programs. And this provides a lot of benefits like we discussed last time. So I'm not going to go through all of those benefits again. Some of them may appear during the course of this lecture, but certainly this illusion of large separate address space is helpful, and it's maintained using indirection and mapping between virtual to physical address spaces. And we discussed what is needed to enable that indirection and mapping, and that's the page table. Page table is very interesting because page table enables address translation. We've seen multiple examples. Again, I will not go through these again. And it exists as part of the operating system, and the hardware is aware of it. Basically, this is part of the contract. This is part of the ISA, essentially. The ISA specifies it, as we will see with some real pictures and copy-paste from ISA manuals. And we wanted to solve some issues with this page table, and one of the issues we tackled was the page table size, right? We said this page table actually can be quite big if your virtual address space is large and your page granularity is small. Small is 4 kilobytes. 4 kilobytes is small. Even 1 megabyte is small with a 64 bits virtual address space, right? So basically, we calculated the size of this page table, assuming this sort of system, and we saw that it's 16 petabytes. And we said that it's not possible to have this in physical memory. So we solved this problem by introducing another level of indirection, which is essentially first level and second level and nth level or multi-level page tables or hierarchical page tables. It's also called hierarchical page tables, as we have discussed. Essentially, you only need to store only the first level page table in physical memory. Everything else can be in virtual memory. And you basically bring the page tables that you need into the physical memory whenever you touch that part of the virtual address space and you need translations for those parts. Makes sense, right? So a page table is enabling translation. If you don't need a translation, you don't need a page table. If you don't need a translation in that part of the virtual address space, you don't need that page table to be brought into the physical memory, essentially. Okay, so that sounds good. Hopefully you're all on board with these. Sounds good? Multi-level. And you can also read your book because this is also in your book, as you can see. Now, I was also giving you examples from multi-level page tables from the x86 manual. We actually went through this. Essentially, this control register 3 is the page directory base register, which is a physical address. And only this page directory table, which is essentially a first level page table, it needs to be in physical memory, and everything else can be in virtual memory. But you can see that you need to translate this to get to another page table and index it using some other bits in the linear address or virtual address to get to the page address or translation. This is the page table entry, essentially, and this gives you the physical page number that corresponds to that virtual page number. Okay, so there's nothing magic about this, and you can actually put numbers. These are real numbers from x86 if you use 32-bit virtual addresses. But x86 is actually a very flexible architecture. It has a lot of baggage because of its flexibility, so you can actually have larger pages as well, 4 megabyte pages, for example. If you use 4 megabyte pages, then your page table doesn't need to be hierarchical, as you can see. Right? It's only single level because your page offset is very large, as you can see, and your directory, or meaning the virtual page number, is actually small. Right? Okay, but x86 is even more flexible. You can actually have 48-bit addresses, and you can have a 4-level page table walk. We've seen this yesterday. This is not the worst, actually, as you will see soon. So, but I want to make sure that this is very clear. This is the reason virtual memory is a hardware-software construct is all of this needs to be specified in this book, which is the ISA, which is, as you can see, at some point it was 4,830 pages. You will see another version with 5,060 pages, but this is a picture that I showed you in lecture 8 or so, where we talked about ISAs, and I said virtual memory management is part of it, right? Access control mechanism, priority privilege, task thread management is part of it. And this is the 5,060 page version of it, which is 1 year later, or 1 year or so later. And there's a specific portion of this ISA. These are actually multiple volumes. One portion essentially is about system management, so system programming guide, right? This is where the system architecture is specified. Page table is an example of it. This is what the operating system designer needs to know when they write an operating system, for example. How do they manage the tasks and threads, as well as virtual memory? And this particular manual is this volume 3, as you can see, and it by itself is 1,500 pages. Now you can see some parts of it. Chapter 2 is about system architecture. Chapter 3 is about protected mode memory management, paging. There's a chapter dedicated to paging. I think this has 50 chapters or so, but it's big, basically. And this is actually specified in the ISA, and this is part of the problem. This is a very rigid specification. It's like a specification of instruction, right? This is what the page table looks like. These are the entries, as you can see, right? If you have 4 megabyte pages, page directory entry looks like this. And this is the for page table entry for a 4 kilobyte page. Looks like this basically. This is the address of the page frame. This is essentially the physical page number. And these are the different addresses, address of the page table, as you can see over here, right? And then there are some other bits that we're going to look at. One of them is the valid bits. So 1 means valid. So if it's valid, that means that the translation is valid over here. You can either go to the next page table address or the physical page number, as you can see over here. If it's 0, that means it's ignored. Then you need to get a page table page fault exception, right? And we've also seen that. We're going to see more of that. But the purpose of showing you this here is this is part of the ISA. Somebody put this up over there. And if you want to write an operating system that does virtual memory management properly on that architecture, you got to build your page table this way. If you build in some other way, you're not obeying the ISA, and the processor is designed to actually look at these bits in a particular way. We're going to cache these bits in TLBs, for example, soon. The processor is designed to actually do the page table walks in hardware. You don't have to do them in software. We're not going to talk about that, but you will see that maybe in future courses. Essentially, if you don't design your software obeying this, your hardware will not work on whatever you designed. If you don't design your hardware obeying this, the software will not work on the hardware you designed. And that's basically, this is the interface over here. It's not an instruction, as you can see. Instructions operate on these memory structures. Okay, so if you go into the specification, clearly there are specifications. We're going to see this again, but present is the valid bit, essentially. x86 has a nice naming strategy. I like the present name also, present absent, right? Okay. And then there are a bunch of other stuff that we will see soon. Some of these are for access protection that we will talk about. Okay, so this is actually the 5-level page table structure that x86 has. There's a 5-level translation as well to increase the address space. But you can see that you first need to get this page table entry. If it's valid, that's good. Otherwise, you get a page fault over here and then bring the page table. And then you need to translate this one, the 2nd level, the next level, which is the 4th level over here. If it's valid, that's good. If not, you get a page fault over here. And then you translate this one, well, one of these actually, depending on how large your page is. Ignore the 1 gigabyte page over here. Look at this one over here. Essentially, you get the address if it's valid. And then you go to the next level. You get the address if it's valid. And then you go to the next level. Finally, this gives you the physical page number. So if someone asks you a question, how many page faults can you get when you're actually trying to get the physical page number of a load that has a virtual address, it could be a lot. It could be 5, actually. And that's to fetch the instruction, potentially, to fetch the load instruction. That's a virtual address, the PC. And then when you actually execute the load, you calculate another virtual address, and then you can get 5 more page faults over there. Right? That's 10. This is all assuming that you don't get a page table entry at the boundary of a page. If you're at the boundary of a page, you may actually get 2 page faults to service something. That, I think, doesn't happen in x86 architecture unless you have some serious misalignment issues, but it could happen in some other architectures. It used to happen in VAX, for example. So you can actually get lots of page faults in this. That's why you actually want to not traverse this page table. That's why we're going to introduce the next idea very soon. Okay, but just to give you an idea, these are the 4 kilobyte pages in x86. These are the 2 megabyte pages, and these are the 1 gigabyte pages. So you can actually have huge pages in x86. And even 1 gigabyte pages, as you can see, require 2-level page tables with a 48-bit address. So if your virtual address increases, your page table, your multi-level hierarchy also increases. Makes sense, right? Okay, so this is one of the reasons it's very difficult to scale the system into very, very huge memory sizes. If you have petabytes and petabytes of memory, it's a lot of inefficiency, basically, that you have in this translation. So people are looking into how do you actually do this in a much more efficient way. Okay, so we solved the first challenge. I actually added a little bit more just to give you an idea of what this is really about. So we solved the page table is large challenge using multi-level page tables at the cost of additional indirection, additional latency. Now let's talk about this latency issue, right? So basically, the second challenge is whenever you do address translation, each instruction fetch or load or store requires at least 2 memory accesses, assuming you get the translation whenever you access the page table, right? And assuming non-hierarchical page tables also. Basically, 1 memory access for address translation, you read the page table. and then want to access the data with the physical address after translation, right? This is the good case, but in the bad case, it could be lots of page faults also, as you can see, right? So with a hierarchical page table, that 2 goes to maybe 4, 5, 6, 7, right? Depending on how many levels you have. But let's assume it's 2. Even 2 is bad, right? You don't want to access memory twice to actually get the instruction. And then you don't want to access memory twice to get the data that the instruction needs, right? You want to access memory once to get the data immediately. Right? So basically, this is a problem. 2 memory accesses to service an instruction fetch or load store greatly degrades execution time. And number of memory accesses increase with multi-level page tables, as we just discussed, unless we're clever. Basically, this is where another part of the hardware comes in. Hardware accelerates this translation process using special caches. So we're going to introduce a special cache. It's called a translation look-aside buffer. How many of you heard about this in the past? Okay, you're hearing for the first time. That's great. You'll hear more in the future, perhaps. But basically, it's a cache. It's caching the page table entries in a hardware structure in the processor to speed up the translation. That's the idea. All of the principles of a cache apply here. TLB, essentially, it's a small cache of most recently used page table entries. In other words, recently used virtual to physical translations. It's a PTE cache, in other words, page table entries, right? It reduces the number of accesses, memory accesses required for most instruction fetches and loads and stores to only one TLB access. So it can be very small, right? It can be small and you access the structure and you get the translation immediately. You don't need to access memory at all anymore because you've cached the translations there. Okay, that sounds good. It's a specialized cache because you do need to do this translation. Okay, so basically, the reason it works is the reason why caches work. Because we have spatial and temporal locality in translations, in page table access, essentially. And you can imagine why, right? You basically are streaming through memory, let's say, and you've allocated, you have a large page, let's say. In that large page, clearly that translation is used many, many times. If you're executing lots of instructions in a sequential manner, they all belong to the same page, right? And then assuming that the next page is allocated in the physical consecutive page in memory, you have, next page is actually in the next virtual memory address, right? So basically, if you're going through the sequentially, you're basically going through the virtual memory address space sequentially. The translations actually have locality as well, spatial locality as well. And temporal locality because you have many instructions accessing the same data in the same page or instruction in the same page. Okay, so this is the reason basically, because memory access have temporal and spatial locality. And large page sizes clearly exploit spatial locality better, just like we saw in caches, large block sizes. Remember that picture that I showed you yesterday? Page is equivalent to block. Essentially, if you have a gigabyte page and if you have very good spatial locality, your TLB hits most of the time, right? Okay, and consecutive instruction on loads and stores are likely to access the same page. We already discussed this. So TLB is a cache of page table entries, in other words, translations. It's small, it's accessed in a few cycles. Typically, it's multi-level also. We have multi-level, we have a hierarchy of TLBs also in existing systems. So we have a hierarchy of caches, as we have seen, and we have a hierarchy of TLBs. One of them handles the data, the other one handles the translations. You may say this is a lot of waste, and I agree. That's true, but that's the cost of making life easy for the programmer, basically. So typically at level 1, you have 16 to 512 entries, and usually it's high associativity, and you get typically 9% hit rates. But it all depends on the workload, right? It all depends on the access pattern. If you're completely accessing memory randomly with no locality in translations, then you get 0% hit rate in this cache, and it's basically terrible. Okay. So hopefully you get the benefit of this, right? This reduces the number of memory accesses to only one TLB access. You don't need to access even physical memory or the page table. Page table resides in physical memory, but you don't need to access it because you already cached it whenever you use the translations. Okay, so let's take a look at an example 2-entry TLB. This is the toy example from your book also. It's essentially a 2-entry cache, right? So what do? Essentially, it caches a translation. It caches the page table entry. Here, we don't have the access control bits. It actually normally caches the access control bits, but your book simplifies things. Essentially, we have 2 entries. Both of them are valid over here. Essentially, the translation looks like this. In each entry, you have the virtual page number and the corresponding physical page number. And in the other entry, you have the virtual page number and physical page number. So this is caching 2 page table entries for 2 different pages, and you know which pages they are. And if the processor is trying to access this virtual address, it consults this TLB, accesses the TLB, and basically you can see that this is a two-way or fully associative cache in this particular case. So it basically searches the virtual page number it's looking for. And this is essentially part of the tag in the TLB, right? And in this case, there's a match on entry 0 over here, or way 0, if you will. And you get the translation, or you get the physical page number, concatenate it with the offset that doesn't get translated, as we've discussed yesterday, and you get the physical address. Okay? So instead of doing the page table access, we replace it with the TLB access. If you miss in the TLB, if you don't have the translation of the TLB, then you do the page table access that we saw yesterday. And then when you do the page table access, you access the page table entry and you bring it into the TLB, right? That's the idea. Just like you would cache data, you're caching page table entries in this case. Okay, no magic. Okay, basically everything we discussed in caching and prefetching lectures apply to TLBs. You can have instruction and data TLBs for exactly the same reasons why we have instruction and data caches. You can have multi-level TLBs for exactly the same reasons why you have multi-level caches. You have associativity and size choice and trade-offs. Again, for similar reasons, you can apply insertion, promotion, and replacement policies. What do you keep in which TLB and how to decide that? You can prefetch into the TLBs. You can assume that you're striding through memory, and you can actually go and walk the page tables and get the translations early. And this can actually work together with the prefetcher, in fact. And you need to keep TLBs coherent if they're in different processors. If one of them modifies the translation for some reason, because the operating system may be running on it, you need to keep it coherent in the other processors that may have cached an older translation. And you can have shared or private TLBs across cores and threads. Basically, everything we said applies here. It's just a cache, except it's caching something special, translations. But because you've taken this course, you know that there's nothing special, right? Everything is bits in the end. You're caching bits, and you need to make sure that those bits are satisfied correctly. We're just assigning meanings to bits in this particular case, and that meaning is a translation. Okay, so clearly we're not going to go into this, but I think you can actually watch more detailed lectures that talk about an example of how modern processors work. We won't have time to do that. We'll release that lecture. You can take a look at it. But modern processors, translation hierarchy is actually quite complicated. There's also hardware page walkers. So actually this walk in x86, for example, whenever you need to do the translation, whenever you need to get the translation, there's a specialized engine that is essentially walking the page table to figure out where the translation is. So you don't do that using a program, you do it using a specialized hardware accelerator inside the x86 processor. Sounds fancy, right? And this is one of the first accelerators that is added to the system, actually, before a lot of other accelerators. This came close to around the floating point times, basically. They added the floating point accelerator, and they also added the virtual memory accelerator, if you will, because virtual memory is so important. Okay, so let's talk about some examples before we end this part of the lecture. Actually, I have a lot of interesting things over here, so we're not done yet. But as I said, virtual memory requires both hardware and software support. Page tables in memory, it can be cached in special hardware structures, as we have just seen. And OS and hardware both know the page table organization and structure through the ISA. The hardware component is called the MMU. If you hear this term, it's the memory management unit. It refers to actually the hardware component, everything that's in hardware. It's not just the TLB. It refers to the page walker and then also the page fault handler, as we will see. Well, part of the page fault handler, I should say. Okay, but it's the job of the software, the operating system, is to use the hardware to populate the page tables, decide what to replace in physical memory. So we're going to talk about some of these things also. And to change the page table base register on a context switch, right? Because when you context switch to some other process, you should really change the translation hierarchy, essentially. And that happens by changing that CR3, for example, the page table base register or control register 3 in x86, so that you can use the correct page table. And it needs to handle page faults and ensure correct virtual to physical mapping. Again, a lot of these are done also cooperatively between the hardware and software, but it's the responsibility of the operating system, because the operating system is the one that's executing the page fault handler, for example. And page fault handling is special because it's an exception. It's an exceptional condition. The process gets a page fault. And normally, if you remember the exception lecture, we said that exceptions are handled at the priority of the process. This is not the case here. Here, you escalate privilege so that you can actually handle the exception, because the page tables are very important, as we will see soon. You cannot enable the user to change it. If you enable the user to change, that's a huge security problem. Basically, you get a page fault. The operating system needs to kick in and basically ensure that the page fault is handled in a secure way so that the mappings are changed without any problem, right? Because if you change the mapping in a wrong way, either the process will access wrong data or a process may access some other data that it doesn't have permissions to, as we will see. Okay, so a page fault is a special exception, basically. Okay, user cannot handle it, I should say it that way. It's the context in which it is handled is the system, not the user. Okay, so address translation, we've already seen this, so I'll go through this relatively quickly. But basically, this dictates how to obtain the physical address from a virtual address. Page size is specified by the ISA. There could be multiple page sizes, as you can see today. This actually causes issues in how to organize the TLB also. We have multiple different TLBs for different page sizes. Now you have a problem, right? So if you're interested in this, you can watch the additional lecture. We don't have time to go over this. So basically, there are trade-offs in the page sizes, similar to trade-offs we have in caches. And page table contains an entry for each virtual page. Basically, it's called the page table entry. Then the question is, what is in a PTE? Let's take a look at that a little bit. And we already said that page table is a tag store for the physical memory, right? Data store. It provides a mapping table between virtual memory and physical memory. And page table entry is really the tag store entry for a virtual page in memory. So you need a val bit, as we discussed, right? This indicates validity or presence in physical memory. You need tag bits. These are the physical frame number or physical page number bits to support translation. You need bits to support replacement, which we're going to talk about soon. What do you replace from physical memory if your physical memory is full? So you need to know which pages are not touched. But this actually is a problem because we have so many pages in physical memory, as we will see soon. You need a dirty bit to support write-back caching in physical memory, and we've discussed this already because write-through is pretty expensive in physical memory. You need protection bits to enable access control and protection. Now, this has nothing to do with address translation. This is basically added to the system because the system is capable of doing more than address translation. So this is completely orthogonal to address translation. You can actually use something else for protection, but today virtual memory functions serves two functions. One is access protection and the other is address translation. And we'll see this more. So this is my nice handwriting. You'll see better pictures perhaps, but basically I already said all of this. Okay, so recall address translation. We've already seen this, so I'm not going to go through this. This is the general address translation form. You get virtual page number translated to physical frame number. And you have a separate page table per process. So we've covered all of this. So let's move to something that we have not fully covered. So address translation, you may get a page hit. So if you think about the MMU can be a structure that includes TLBs. That does include TLBs, actually. You send the virtual address to MMU. MMU somehow responds with a translation. And if it's a hit, meaning it either hits in the TLB or the page is in physical memory, meaning it's there's a page table entry that's valid for that virtual. Hits can be classified as TLB hit and TLB miss earlier, as we discussed also, right? So basically, in this case, there's no page fault. Everything is good. You get the translation after either a TLB access or a TLB access plus multiple memory accesses to get the page table entry. Now let's talk about page fault. This is not something we have not talked about so far. Let's see how it's handled. So the processor sends the virtual address to the memory management unit. It misses the TLB. It misses the basically in the end when you figure out the translation doesn't exist. Either one page table doesn't exist that you're looking for. Doesn't exist meaning isn't present in physical memory because it's present in disk somewhere, or basically the real page that you're looking for isn't in physical memory. So you need to handle the page fault in this case. Essentially, val bit is 0. There's a page fault exception that's triggered. Once a page fault exception is triggered, a page fault handler kicks in. It first, assuming the physical memory is full, it first evicts some dirty page out to the disk, for example, assuming it's going to replace that. And then handler pages a new page and updates the page table entry in memory. And then it returns control to the original process, restarting from the faulting instruction that caused the fault. And hopefully that gets a page hit and hopefully a TLB hit because you filled all of those when you handled the fault. So let's take a look at how this is handled a little bit. So basically, this is a miss in physical memory, if you think about it, because physical memory is a cache of the disk. essentially page table entry indicates virtual page is not in memory. Access to such a page triggers this fault exception, and we invoke the OS exception handler. Other processes can continue executing, right? This process needs to stop. But now you know about run-ahead execution. So maybe you can actually do run-ahead execution software also. Actually, this is a real proposal. It's a beautiful proposal that showed benefits. I'm not going to go into that. So you can actually speculatively execute the process at the software level. If you critically think, you can actually apply a lot of the concepts that we've used into software as well. Okay, so let's not go into that right now. But basically, OS has full control over page placement. So basically what it does is before fault, the CPU is accessing this virtual page. It's on disk. It's not mapped to memory. After the fault is handled, the CPU is accessing the same page again. And now the page is mapped into physical memory, right? And the page table is fixed to reflect that. And something is kicked out from the physical memory, perhaps, right? Okay. So how is this serviced? Again, there's a lot that's involved here. Now we're going out to the system level a little bit more. If this course continues to, in the next direction, there's actually a lot in the system level also to think about. But basically, processor signals the I/O controller initiated by the operating system. Operating system basically tells the I/O controller, I want to read some block from disk. This is the address of the page table that I want from the disk. And I want to store it to memory starting at address Y, because that's where I want to locate the page table, right? Because I know the mapping and I'm going to make sure everything works. And there's a disk to memory read occurs, and this is usually handled using direct memory access. There's a setup that happens in the memory controller, and the memory controller automatically transfers from the disk, or disk and memory controller automatically transfer things to memory without involving the processor. This is one of the cases where we don't involve the processor actually, because there's a lot of data that may be transferred from disk to memory. It could be 1 gigabyte as we have seen, right, with a large page. So this happens under the control of the I/O controller. And eventually this finishes, the controller signals completion and it interrupts the processor saying that operating system, I'm done. So you can actually resume the process that that faulted on this page. And the operating system fixes all of those mappings and resumes the process. Makes sense, right? So you can clearly see that this can take lots and lots of microseconds, milliseconds. Actually, milliseconds are more. So you don't want page faults in your system, basically, the takeaway. Okay, so let's talk about page replacement algorithms. If physical memory is full, you have a problem at hand. Now you need to actually replace one physical frame because you're trying to bring some other physical page into the physical memory, right? So how do you determine physical memory is full first? Usually you have a free list of physical pages. These are operating system data structures. Operating system actually keeps track of these. You can potentially cache these in hardware, just like we've been caching stuff in hardware. But essentially, it's possible to keep track of these. So of course, we've done this exercise before. Is true LRU feasible? We said that it's not feasible even in caches, right? Or small caches. Now let's take a look at the size of this cache. I'm going to take 1 terabyte memory because this is almost reality today, right? We're going to have 1 terabyte memory soon. 1 terabyte is how much? Is it 2 to the 40 bytes? I think so. Yeah, tera, peta, exa. Okay, tera is 2 to the 40. 4 kilobyte pages, small pages, 2 to the 12. So essentially, we have 2 to the 28 pages. How many possibilities for ordering there if you want to actually do perfect LRU? Now you know the answer by heart, 2 to the 28 factorial. Now that's a huge number. You can probably figure out what that number is in terms of, and write it down, but it'll be a waste of paper, let's say. Essentially, it's a huge number. So modern systems, again, use approximations of LRU for 2 reasons. One of these reasons is this, and the other is LRU is not a perfect predictor of future anyway. Right? So I'll introduce the clock algorithm very quickly, because the algorithms here need to deal with 2 to the 28 pages, right? How do you figure out which one should you evict? Whatever heuristic you come up with is actually not so easy to implement in the end. So clock algorithm is very clever. But there are more sophisticated algorithms that people develop. Actually, usually it's a more sophisticated algorithm. This is a nice algorithm from IBM that was published about 20 years ago now. It's adaptive replacement cache. They call it cache, but it's really managing the physical memory. Physical memory is a cache, as you know. So what is clock algorithm? Very quickly, it resembles a clock, basically. Essentially, you have all of these pages in physical memory. Imagine 2 to the 28 of them. I'm showing you some small number over here, and this is one of the nice pictures I could find. But basically, clock algorithm has all of the pages like this. It points to one page at some point, let's say. And let me actually say this. You keep a circular list of physical frames or physical pages in memory. OS does this, of course. And it keeps a pointer or hand to the last examined frame or last examined physical page in the list. When a page is accessed, the clock algorithm sets the R, referenced or accessed bit in the PTE for that page, saying that I recently accessed this page. Okay, that's good. Now, when a frame needs to be replaced, this clock algorithm kicks in and it replaces the first frame that has the reference bit not set. And it finds this frame by traversing the circular list starting from the pointer going clockwise. So if you look at this example, we're pointing to 0. This is not set. That's the reference bit. So you replace this one, okay, if you need to replace something. And then you change the clock algorithm to this one, okay? And then this is not set. If you're going to replace, that's going to be replaced next. And then this will point to 1 over here. You're not going to replace whatever is 1. So you go and find the first 0. Makes sense? Basically, the goal is to find the first non-accessed or not recently accessed page, physical frame. So during traversal, while you're traversing this, if you're skipping some page that has been recently accessed, that is a bit set to 1, you set it to 0. Meaning, I've seen this page, it's recently accessed, I'm not going to replace it, but because I have gone through it, I'm going to set it to 0, saying that next time I see it, if it's still not accessed, I'm going to replace it, okay? And of course, you're not going to get to that for a while, assuming you have 2 to the 28 pages to go through with the sand, right? Okay, so this is a very rough approximation, and it's been used in early Linux kernels. Variants of it are still used, frankly. And then you set the hand pointer to the next frame in the list. Makes sense, right? So this is clearly an approximation so that you don't replace the recently accessed pages. And again, there's an interesting thing over here. There's an R bit in the PT, page table entry. This is also specified by the ISA. The ISA basically specifies an R bit, I will show you, in x86 called the A bit, accessed bit. And this needs to be set. So how do you set this? You set it in the TLB. How do you propagate the entry to the page table? When you actually set it in the TLB and you need to replace something in the TLB, you need to write to the page table. So they're actually really interesting things of management over here. And when you write to the page table, you need to do memory accesses, right? Okay, so keep things in mind. These things complicate memory management in general. So basically, what we're doing is we're trying to make life easy for the programmer, but we're adding a lot of memory accesses while doing that, as you can see, right? Okay, so there are differences between cache, like hardware cache versus page replacement. Physical memory is a cache for disk, as we've seen. It's managed by the system software via the virtual memory subsystem. Page replacement is very similar to cache replacement. Page table is a tag store, as we've discussed. The difference is essentially multiple. The required speed of access to the cache versus physical memory. So this page replacement can be slow. It doesn't need to be very fast, if you will, because caches require cycles, accesses that need to be as quick as cycles. Here, we're talking about bringing the page from memory all the way into, from disk all the way into memory. You can have your sweet time to figure out what to replace, right? Because that's going to take at least microseconds. Okay, so number of blocks in a cache versus physical memory. Hopefully we've seen that. I just give you an example with 2 to the 28 blocks in physical memory or pages. So this makes a complicated physical memory replacement algorithms are not easy to implement. I think we already discussed this. It's similar to the first one, which I'm not going to talk about. And then the role of hardware versus software. Caches are hardware managed because the latencies are low, but this is mostly under the control of software. But as I said, it's accelerated in hardware. Okay, any questions? I'm going through some of these relatively quickly. There's a lot of complexity in the system, actually. But if you watch the lecture that talks about what is done in a real system, I give Intel Skylake as an example, you'll see there's even more complexity than what I'm talking about. That's one of the reasons why we believe as researchers that this needs to be rethought completely. But of course, the difficulty of rethinking something that has been around for 60 years is not easy. Because the infrastructure has been developed for 60 years, programs have been written this way. If you actually do something completely different, it's going to be not easy to adopt, right? Okay, let's talk about the memory protection aspects of virtual memory. And I like this part because I get to talk about RowHammer here also, as you will see. But this is actually interesting because memory protection is necessary, right? Multiple programs or processes run concurrently. Each process has its own page table. Never forget that. Each process can use its entire virtual address space without worrying about where other programs are or what they're accessing. This is beautiful, right? A process can only access physical pages mapped in its own page table, cannot overwrite the memory of other processes, basically. And this enables essentially isolation, right? You're isolating processes from each other. And it provides protection also. But protection has other categories also, because within a process, you may be able to read a page, but not write it, right? Within a process, you may be able to read and write a page, but not execute it necessarily. So you have different permissions on a per page basis. For example, if you don't want your programs to be modified, you can have read access to the code, but not write access to the code, right? If you don't want someone to execute, write to some place and execute that data that will be interpreted as instructions when you jump to it, you basically mark it as non-executable, right? So basically, you can enable access control mechanisms per page this way. Okay, so remember page tables per process. We've seen this. So essentially, access protection and control can happen also via virtual memory. And this is called page level access control or protection. Essentially, not every process is allowed to access every page. For example, you need supervisor level privilege to access system pages. An example of a system page is a page table. All of those page table structures are system pages. As a user, you should not have any access to it, right? Otherwise, you can change your permissions to access anything, right? For example, you may not be able to execute instructions in some pages because you're not allowed to execute that code, right? And the idea is, to enable this is to store access control information on a page basis in the process page table, right? And enforce access control at the same time as translation. That's the idea. It works nicely because that's when you really need to enforce access control also. When you're trying to access a page, you also need to translate it. And assuming you have permissions, translations, you can proceed with translation. If you don't have permissions, don't even proceed with the translation, right? Basically, virtual memory system serves two functions today. One is address translation to give you the illusion of large physical memory, and the other is access control to give you memory protection. And this is my nice picture. Essentially, when you're doing translation, you also bundle access control with it. And in fact, access control takes priority. If you don't have access, forget about the translation, right? You don't need the translation. And if you're trying to access a page that you don't have the proper access to, you'll get an exception immediately. It's called an access protection exception in some systems. Essentially, you get kicked to the operating system, and the operating system basically tells you this usually stops the program, right? Because it's trying to access something, it's not allowed to access. Okay, so you can see that this is an example. We extend the page table entries with permission bits. This is a very simple example, right? In addition to the translation information, we have read-write permission bits. And then, of course, there needs to be val bits, etc. Right? Okay, so different processes have read and write access. You can see that they're sharing physical page 6 over here. It could be a shared library that they're executing. It could be some shared data. Again, it needs to be set up through the operating system to be able to do that. And they may not be sharing some other processes. For example, physical page 9 is not accessible by this process. And you may have read-write permissions to some of these pages and not write permissions to some of these pages. So basically, it depends on the specification of the ISA again, what you can do. So there are privilege levels in x86. Usually, again, I don't have time to go over this in detail, but there are these levels that you may see. They're not necessarily the best architecture for protection. This is old, let's say. But just to give you an idea, usually at ring 0, you have the supervisor level, highest level. Operating system has this privilege. And usually user applications are at the lowest privilege, right? User. Supervisor is kernel in modern terminology. It used to be called supervisor in the past. Okay, so let's take a look at these page directory and page table entries a little bit more closely. So if you look at, this is a page directory entry in x86. This is the first level page table. You get the address of the page table, and you have a bunch of bits over here. So this is the address of the page table, and these are the flags. You can see that one of them is read-write, one of them is user supervisor. You have the same thing over here at the PT also, read-write, user supervisor. So now you can actually have protection at larger granularities also. So at the larger granularity of a huge page table, as opposed to a page, you can specify user and supervisor level privilege as well as read-write accesses because of the multi-level nature, right? So this multi-level nature enables also multi-level access control, if you want. It gets hairy a little bit, as we will see. Basically, this PDE protects all 1024 pages in a page table. You can see these are the bits that I mentioned over here. Read writes, whether you have read permissions or write permissions, or user and supervisor permissions. Whereas PTE protects one page at a time. Granularity is smaller over here. Okay? And this is basically the specification of the ISA. Now you can see how messy this gets a little bit, right? Basically, depending on what you have in the page directory entry and page table entry, there's a combined effect of whether or not you can access. And we can look at that over here. Again, I don't have time to go over this, but basically this is what the ISA specifies. And the operating system needs to obey it, and the hardware needs to obey it. Period. If they specified it wrong, too bad. Fix the ISA somehow, right? Okay. So any questions on this? I'm not suggesting this is the best architecture for protection, but this is what we have in common systems usually. ARM has its own protection mechanisms, which is slightly better, but not too much better if you ask me. This is what we do today. There could be better, stronger protection mechanisms that are a lot more costly to implement. Let me put it that way. Now, what if, let's talk about RowHammer a little bit. What if your hardware is unreliable and someone can flip the access protection bits? This shows how flaky some of these access protection is, as we will see. And this is also going to have some implications on how important some of these issues are, in my opinion. Such that a user level program can gain supervisor level access. In other words, access to all data on the system by flipping the access control bit from user to supervisor. That's one way to do it, right? You somehow flip the access control bit on your page table entry to supervisor, and you have access to your page table, because this page table entry may be pointing to your page table, right? Makes sense. I'll give you an example. Can this happen? Well, since you know about RowHammer, you know that this could happen, right? So basically, you can predictably induce errors in most DRAM memory chips. And we already talked about this. Let me give you the idea very quickly again, and then I'll show you a security attack that actually takes over the system by taking advantage of these bit flips. So basically, the issue was whenever we activated a ROV, we would apply high voltage to it. Whenever we pre-charged a ROV, if you remember from DRAM lectures, we would apply low voltage to it. Now, if you keep doing this repeatedly in the memory controller by accessing memory, you would get bit flips in pages that are adjacent, physically adjacent. Right? Clearly, this should not happen. You can say that this is bad, data corruption, blah, blah. But this is actually a security problem also. And as we discussed in an earlier lecture, we said that most DRAM chips are vulnerable. Actually, all DRAM chips are vulnerable today. So let's take a look at an example. This is a user-level example. When we first published the paper, we actually put this code online, and then later Google actually took this, improved it, etc., as we will see. This code, what this code does is, it essentially hammers X and Y, address X and Y. It selects address X and Y in some way. They map to the same bank, and it avoids caches to X and Y. Flushes X and flushes Y from the cache, and it avoids row hits to X and Y by reading Y in another row. Basically, we got to get rid of the caching, right, in the system. How do you get rid of the caching? By flushing these cache blocks that you're touching in rows X and Y, and also getting rid of the row buffer by opening different rows in the same bank. So basically, what this program does is this. It keeps repeatedly accessing rows X and Y. Sounds good, right? You can actually try this program if you want. I'm curious if it still works. There are better programs out there today. This is 2012, remember. Okay, so you get bit flips. And these are real bit flips. They're reproduced in real life. And now we're going back to how it's related to memory. So if you look at the paper that we wrote in 2014, it says memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And virtual memory actually ensures this, right? Virtual memory is great because it ensures this, but unfortunately, virtual memory is powerless if you have a bit flip at the underlying levels like this, right? So we said in this paper that someone can hijack your computer if someone is maliciously trying to take advantage of these bit flips. And these folks from Google Project Zero essentially did this. Essentially, they took the program that I showed, they improved it, they made it better, and they wrote this blog post. I have a copy paste from this blog post, and they also published a talk that you can watch their video in the Black Hat conference in 2015, where they said that they tested a selection of the laptops and they replicated the issue that we discussed. And they built two attacks. One of them is taking over the Google native client, not so interesting. The other is actually doing attack on the virtual memory subsystem, as we will see. Essentially, these are all their own words. They use RowHammer-induced bit flips to gain kernel privileges on x86 Linux when run as an unprivileged user-land process. So they were able to induce bit flips in page table entries. And they were able to gain write access to the own page table of the user level process. And if you gain write access to your own page table, you can change anything you want, right? So that's the idea over here. So let's take a look at how they did it actually, because now you have, I think, the background to understand this, at least at some level. These are their slides. They basically say, essentially, what we've said earlier, right? Page table entries are dense and trusted. They control access to physical memory. A bit flip in a page table entry's physical number can give a process access to a different physical page. Aim of the exploit is to get access to the page table, write access, I should say. Read access, okay. You cannot do too much with a read access. Write access, you can do a lot. And gives access to all of physical memory if you do that. And they want to maximize the chances that a bit flip is useful. So they're actually going to introduce a special attack. It's called page table spraying. They spray the physical memory with page tables, and they do it in a clever way, as we will see. And they check for useful, repeatable bit flip first so that they can actually exploit this. So this is the page table entries that they exploited. Basically, it has 64 bits over here. And they basically say if they actually target this read-write bit, the chance of bit flip is low, right? Basically, the chance of a bit flip landing here is 2% because that's 1 out of 64. Whereas if they target the physical page base address, which is the physical page number, let's say, essentially it's 20 bits. So you get a 31% chance to be successful to have a bit flip over there. So it's a probabilistic attack in the end. And these are, again, their slides. You can watch their talk as well. So let's see what they did, basically. So this is the virtual address space. This is a physical address space. We should be very familiar with this injection right now. So they say, what happens when we map a file with read-write permissions? This is what happens, basically. The file gets mapped to memory, and it has a virtual address. And then the file, the bits of the file is in physical memory, actually. But it happens through an injection, which is a page table. Those red entries are page table entries that map the virtual pages of the file to the physical frames in physical memory. Sounds good, right? Okay, so what happens when we repeatedly map a file with read-write permissions? You get more page table entries. You get more page tables, essentially. Because this is the same file, yes, but these are different processes that are mapping. Or different, whenever you actually map the different files, it acts as if you have different page tables that are needed because they need to be, they actually, you modify them using different streams, if you will. So basically you get many, many page tables in memory, right? Pointing to the same physical frame over here. Okay, basically PTs in physical memory help resolve virtual addresses to physical pages. This is their words. And they can fill physical memory with page table entries. So most of physical memory is page table entries. Now this is good. Each of them points to pages in the same physical file mapping. So all of them point to this green part over here. Now, if a bit's in the right place and the page table entry flips, the corresponding virtual address now points to a wrong physical page with read-write access because we opened the file with read-write access. We're able to write to this. So this page table entry tells us, whenever we access this virtual address, this page table entry tells us, you can write to this part of the file that's cached in physical memory. That sounds good. But if I do a bit flip by doing a RowHammer attack, I can actually flip the bit in the physical page number in the physical page table entry over here to somewhere over here. So I gain access to some page table entry over here because I sprayed the memory with page table entries. That sounds good as an attacker, not as a defender. Basically, chances are this wrong page contains a page table itself, which is true because you sprayed most of the memory with page tables. An attacker that can read-write page tables can use that to map any memory read-write. Essentially, you have control of many page table entries over here, and then you can actually do whatever you want to the system. You can change the operating system if you want, right? Basically, you become root at this point. Makes sense, right? So, okay, so to make this a working probabilistic attack, they basically say you need to do other stuff also, like allocate a large chunk of memory, figure out which locations are prone to flipping due to RowHammer, and then check if they fall into the right spot in a PTE for allowing the exploit. So they don't want to leave it to 31% chance. They want to actually see where the bit flips are. You can actually figure that out. And then return that particular area of memory to the operating system. So as a user, you can actually learn a lot about memory and then return to the operating system. And the operating system allocates a page table entry over there later. right? And then you exploit that. And then you force the operating system to reuse the memory for PTs by allocating massive quantities of address space, like we discussed earlier. And then you cause a bit flip using RowHammer that shifts the page table entry to point to the page table, and then abuse the read-write access to all of physical memory. At this point, you are root, basically. Clearly, in practice, there are many complications as they see. So that's essentially what RowHammer circumvents, as you can see, right? And there are many, many attacks that are developed. This is the first attack that shows this, but there actually people have automated some of these attacks today. Okay, so I can talk more about RowHammer, but we don't have a lot of time. But I will tell you that there are a lot of other attacks. We don't have time, and this is actually some works that introduced both attacks and defenses in 2023. There are sessions on RowHammer in the Security and Privacy Conference, for example. Okay, so if you're curious, there's a lot that's being written over here. You can read papers, solutions that were developed by industry doesn't work, which we don't have time to talk about. I'll refer you to a lot of lectures over here. It's hard to guarantee RowHammer free chips, actually. This is a technology scaling problem, and industry adapt solutions are actually quite poor. We will talk about that. But these attacks are actually, industry is also introducing attacks. Like Google itself introduced this half double RowHammer attack. So it's a little bit different from the original RowHammer attack. What they do is you have the victim rows over here, and you have an aggressor row that's not immediately adjacent. Basically, they hammer this adjacent row that's a little bit farther. There's another row in between. They hammer this a lot, they hammer this little, and they cause bit flips in the victim. This basically shows that the RowHammer effect is getting worse in the physical memory. And it's also interesting for other reasons that we don't have time to talk about. But Giray is sitting here, and he can talk to you a lot about that because he's been doing a lot of work on RowHammer, and he's one of the authors in this paper, as you can see. Okay, so the good news is industry is developing solutions to this. This is actually finally, like 9 years after the original RowHammer paper. This is a paper from SK Hynix that was written in ISSCC this year. They basically say, we're trying to solve RowHammer. Yeah, you can see how they're trying to solve. Some of these solutions resemble the solutions that we have proposed in the past. And similarly, Samsung has written papers also, and they modify the DRAM basically. They modify the DRAM to be more intelligent to try to detect these attacks. And this is a paper that was written by Samsung doing something similar, much harder to read paper, let me put it that way. But essentially solutions similar to what we have been discussing. So are we now RowHammer free? Let's see. There's more coming up, as you can see. We're going to present this work at ISCA. I believe there's even more that's going to come up. I think it's not going to be easy to get rid of some of these issues. And it's going to be harder and harder to actually prevent these bit flips in a fundamental way. I cannot reveal the paper right now, but after ISCA, talk to me. So as you know, I talk a lot about RowHammer, and some of your creative fellow prior students realize this. Okay, so if you're interested, there's a lot to discuss here, including some of the solutions, but I don't have time. But I had to put it in the virtual memory lecture because it actually brings together multiple concepts, right? So let me, I'm going to use a few more slides and then conclude, and then we're going to take a break. But basically, this actually opens up some really interesting things. RowHammer actually opened up a lot of hardware security research. Essentially, if hardware is unreliable, your higher level security and protection mechanisms may be compromised completely, right? This basically indicates that the root of security and trust are actually at the very, very low levels. If you don't have some security at the very low level, then you're not going to build secure mechanisms at the higher levels. So you can do as much as you want at the operating system level, it doesn't matter. Because someone will cause a bit flip in some way and circumvent those mechanisms, right? Basically, the root of security is really in the hardware and the physics itself. And RowHammer, Spectre, and Meltdown are recent key examples. I don't cover Spectre and Meltdown. You actually have the background to think about Spectre and Meltdown because you know about caches, you know about speculative execution, you know about branch prediction, all of those, but it's more complicated than RowHammer. It's harder to exploit also. So then the question becomes, what should we assume the hardware provides, right? How do we keep the hardware reliable? Should we assume hardware is completely unreliable and build mechanisms of trusted execution on top of it? That's another approach. This is possible, but it comes at very high costs. It comes at checking, for example. Every time you access a page, you check whether integrity is compromised or not. And that's expensive, basically. And for that, you need some hardware support also. So how do you design secure hardware? How do you design secure hardware is not a difficult question if it's just that. It's a difficult question, how do you, if you actually want high performance, high energy efficiency, and convenient programming at the same time, and low cost. Actually, if you add any of those, secure hardware and high performance, they don't go well with each other. secure hardware and low cost, they don't go well with each other. That's the problem, basically. So basically, there's plenty of exciting and highly relevant research questions over here. And if you're interested, there's more in future courses. Now, let me summarize virtual memory. I think this is a good place to summarize virtual memory and talk about some challenges. So essentially, virtual memory gives us the illusion of infinite capacity, infinite in quotation marks, because you're still limited by the virtual address space size. But hopefully, that's large enough. You have a subset of virtual pages located in physical memory, and a page table maps virtual pages to physical pages. This is address translation. A TLB and also a page walker speeds up address translation. Hardware accelerators, basically. Accelerators specialized for virtual memory acceleration. And multi-level page tables keep the page table size in check. And using different page tables for different programs and having access control bits provides memory protection. This is virtual memory in one slide, let's say. There's more in virtual memory, but we will not cover them. Like, how do you handle virtualized systems? I'm going to show you another picture. This makes the injection to a next level. This takes the injection to a next level. Like if you're running a virtual machine on top of a guest operating system, or if you're running a hypervisor on top of a guest operating system, there's another level of injection over there, as you will see soon. You can have alternative page table structures that may be faster, that may be more useful. Again, we don't have time to talk about that. In fact, in replacement, I ignored an issue. How do you do the mapping from physical pages to virtual pages? You need actually some inverse mapping also to do the replacement so that you can actually change the page table entry. So physical table, page table provides a forward mapping, virtual to physical. But if you're replacing something in the physical domain, you need the inverse mapping. When you replace the physical page or physical frame, you need to invalidate the virtual mapping, right? So you have another problem, basically, which we kind of glossed over, right? We didn't even talk about it, but that problem exists. And you need to solve it if you're writing an operating system. So people have come up with inverted page tables, for example. That's another overhead, as you can see. So that's one of the reasons why we think rethinking virtual memory is actually a good idea. Maybe not so easy. But let's take a look at this virtual memory in virtualized environments. How many of you use virtual machines? Okay, that's good. So many of you, actually, if you submit jobs to cloud, you can actually run virtual machines or your machines here. So basically, this adds another level of address translation. So you have a guest operating system, virtual machine, you have a host operating system, and you have a CPU. Clearly, we've looked at a real machine, right? Real operating system. You have this address translation. But guest also has a virtual addresses, and it gets mapped to the physical addresses over here, which is essentially the virtual addresses from the perspective of the host over here. So you basically have another level of address translation over here. And existing machines, to speed up virtual machine performance, have hardware support for this multi-level translation also. AMD introduced it in 2006 or so, for example. So basically, it's a mess, as you can see, right? It's not that great, but we keep adding infrastructure to support it because it's so important. Okay, so regardless of all of its shortcomings, virtual memory is actually one of the most successful examples of architectural support for programmers. How to partition work between hardware and software hardware-software cooperation in the end. And also the programmer-architect trade-off. The trade-off is made so well that we keep adding complexity to our systems so that we ensure that programmers don't know about what's going on, right? So in that sense, it's not a good deal for the architect, let's say, but it's a great deal for the programmer. Okay, so going forward, how does virtual memory scale into the future? Basically, it's not going to scale easily. It's a lot of energy is actually spent on virtual memory address translation, a lot of cost, a lot of performance, etc. We usually ignore this cost. We don't even count it when we talk about it, right? So physical memory size are increasing, both local and remote. We have hybrid physical memory system, DRAM, non-volatile memory SSDs. We want to actually do that going into the future. There are many accelerators in the system accessing and addressing physical memory. And we have virtualized systems, as we've discussed. And in the future, we already have some near-date accelerators and processing in memory systems, which we may get a chance to talk about in the next part of the lecture if we have time. Let's see. But basically, scaling, this is not easy. Again, we don't have time to go over it, but we are thinking of alternatives to the conventional virtual memory framework. I think this is a very nice direction to think about. I don't have time to talk about it, but this completely rethinks the virtual memory subsystem. You get rid of the virtual memory abstraction and try to make it more flexible, if you will. It has a lot of downsides. Clearly, it has a lot of issues that need to be solved still. But virtual memory has been around 60 years, and new alternatives have been popping up maybe once every 10 years or so. So we need new alternatives to this. And if you're interested, you can actually look at the lectures related to this. So you can see this actually lists some of the challenges. Like rigid page table structure is actually pretty bad in my opinion. We need to fix that somehow, but let's see what happens. So there are more lectures on virtual memory. We don't have time to talk about. But as I said, we'll release one lecture if you want to go into more detail about a real system, how it does virtual memory, and you'll see even more complexity over there. Any questions on virtual memory? Let's see how bad we are on time. Okay, not so terrible, but not so good also. So let's take a break until 28, and then we will have a brief conclusion.
Now we're going to talk a little bit more about issues in virtual memory, but some of which we've already talked about. So these are some extra slides for your benefit. I'm going to go through some of them quickly. But we already discussed how large is the page table and how do we store and access it. I'm going to give you a little bit more example from real systems with some additional slides, but we're going to skip some of the slides. The second question is, how can we speed up translation and access control check? Again, we've discussed this, TLBs, but again, these are very important. That's why I raise up these questions. And then there's a third question, which was brought up by one of you in the last lecture, I think. When do we do the translation in relation to the cache access? And that's going to be important. I'm going to give you a teaser of that, but we're not going to go into the details. There's some backup slides and some lecture references you can take a look at. There are many other issues in virtual memory that we will not cover in detail. I mentioned some of those actually while we were discussing some earlier issues. What happens on a context switch? How can you handle multiple page sizes in an efficient manner, etc. We're going to touch upon some of this when I give you a real world example, but not in great detail. So issue one is, how large is the page table? Where do we store it? In hardware, physical memory, virtual memory? I think we've already discussed these questions. With multi-level page tables, part of the page table is in physical memory, and the rest is in virtual memory, and some of it is not allocated also. And how can we store it efficiently without requiring physical memory that can store all page tables? And the idea is multi-level page tables, as we have discussed, right? And this is the slide that I'm showing you for the fourth time, perhaps, because we have seen it in the last lecture also. And we've already discussed the solution. And we discussed how to do the page table access. There's a page table base register. There's also a page table limit register so that you don't exceed the virtual memory that you're accessing. If virtual page number is out of bounds, it exceeds the page table limit register, then the process did not allocate the virtual page. So there's an access control exception that happens based on that as well. So there's hardware checks. x86 actually has segmentation also, as we discussed in the last lecture, which is a different level of protection, but it's not as important today. That's why we don't talk about it as much. Okay, we already discussed that page table base register is a part of process context. It's an architectural register, and it needs to be loaded when the process context switched in. If you don't do that, then you have a problem, basically. And it's the hardware's job to do that. If you don't do that, actually, the process will be using somebody else's page table base register, and you basically compromise security and privacy right away, right? So the hardware bugs at any level of this process can directly affect your security and privacy, basically. Okay, I've already given you these examples. I'm actually going to skip to the page table entries that are more, so these are more recent. This is x86-64. You can see that page table entries have increased to 64 bits. So they used to be 32 bits over here. Each of these are page table entries. And you can see that now they're 64 bits. Why? Because we need to be able to address larger and larger virtual and physical memories. And so you can see that there are different types of page table entries, CR3. There's possibility of 5-level paging in x86-64. So this is a 5th level, which is they don't call it the directory anymore, of course. This is the 1st level if you have 5th level. This is the 1st level if you have 4 levels. And you can see that there are 1 GB page frames also. So there are 3 types of pages in x86 right now: 1 GB, 2 MB, and 4 kilobytes. And you need to choose which page you want. This is a tough choice, not an easy choice, or the system needs to choose for you what type of page they want. And again, it's a tough choice, basically. It depends on your locality characteristics and your translation, right? And you can see that the other flags also exist. There's nothing special that I want to provide over here, other than this is the 4-level paging example that I showed you earlier, right? We're not going to go through this again, but existing systems are complicated multi-level page tables. This is 4-level paging for 4 kilobyte pages, I should say. This is 4-level paging for 2 MB pages. So it's, and this is 4-level paging for 1 GB page. So clearly for 1 GB page, you actually don't have 4 levels, right? You have 2 levels over here. And you have 3 levels for 2 MB pages, but this is the 4-level paging is the name of the paging mechanism that they use. That's why it's called all 4-level paging. The maximum levels is 4 with the smallest page size. Okay, so that's how large is the page table and how complicated it gets, basically. So how can we speed up the address translation and check? We already know about translation look-aside buffers. We've already talked about how to make it fast. Let's talk about who manages it, meaning what if you miss in the TLB? So TLB caches the recent access translations, the recent translations, but what if you miss in the TLB? What TLB entry do you replace? Clearly, it's a caching decision. Who handles the TLB miss, hardware versus software? And there are advantages and disadvantages to this. In many systems today, hardware is increasingly handling the TLB misses, but there are actually some systems that handle the page TLB misses in software, like MIPS actually handles TLB misses in software. And that gives more flexibility to the system. And we're going to talk about the trade-offs. And then what should be done on a page fault is, what if you actually find out the PTE eventually and figure out that it's a page fault? Then what virtual page do you replace from versus physical memory? These are different events. I want to emphasize that TLB miss is very different from page fault. TLB miss is that says that the translation is not cached in the TLB, in the hardware TLB. Page fault means that the physical page corresponding to this virtual page is not mapped in physical memory. It doesn't exist in physical memory. So you need to bring it. You may get a TLB miss that doesn't result in a page fault, obviously, right? You can actually have a valid page table entry. You may get a page fault that doesn't result in a TLB miss. That also happens if the page table entry is cached in the TLB, but it becomes invalid for some reason. And there are reasons for it, for TLB coherence reasons, for example. When you, for example, replace the page that is subject to the translation, you may actually invalidate that TLB entry. It depends on how you invalidate exactly the TLB entry, of course. But this is certainly possible also, depending on how you implement things. But it's more rare, of course. So who handles the page fault? It's usually the software, basically. Hardware can potentially accelerate it, but so actually, I should say it's cooperative, but it's done under the supervision of the software, basically. You usually have an exception that leads you to a software handler, and the software handler decides what to replace and how to handle the page fault. Usually, hardware handles the TLB, but not always. Okay, we already discussed the TLB. This is a more generic explanation, so you can take a look at it. But basically, the TLB is small. It cannot hold all PTs. Some translation requests will inevitably miss in the TLB. So you must access memory to find the required PTE. This is called walking the page table. Essentially, you walk all levels of the page table in a multi-level page table to get to the PTE, page table entry you're looking for. And this takes a long time, as you know, right? There's a large performance penalty. So better TLB management and prefetching can reduce TLB misses, just like better cache management and prefetching. But then eventually you get a TLB miss. Who handles that TLB miss? Is it the job of the hardware or software? Meaning, whenever you get a TLB miss, do you take an exception or does the hardware handle it? So there are multiple approaches. It's hardware managed in most systems today, x86, ARM, etc., for example. And hardware does the page fault. Essentially, it walks through all of the page table accesses, and it fetches the PTE in the end and inserts it into the TLB. If the TLB is full, the entry replaces another entry. It's basically you do the replacement. And it's done transparently to the system software. This way, you can employ specialized structures and caches, for example, page walkers and page walk caches that we will see in an example soon. Approach 2 is software managed. MIPS, actually, the architecture that you are implementing, does it, except you're not implementing the virtual memory part. The hardware raises an exception, and the operating system does the page walk using some instructions. You can clearly do that, right? You can clearly construct instructions to access page tables, and the operating system fetches the PTE, and the operating system inserts and evicts entries in the TLB. Essentially, this is software managed TLB. And clearly, there are trade-offs to this approaches, and you can imagine some of the trade-offs. Hardware managed TLBs, there is no exception on TLB miss. Instruction just stalls. Other instructions may already be going on in an out-of-order machine. That's great. Independent instructions may continue. And there are no extra instructions, data brought into caches. You don't do a context switch to a software. So that's the big advantage. And that's why hardware managed TLBs are commonly used today. But then the downside is page directory and table organization is etched into the system. The hardware needs to implement that. And if you change it somehow in software, your hardware that manages the TLB is useless now. So OS has little flexibility in deciding the TLB organization and page table and directory organization. Software managed TLB, of course, doesn't have that disadvantage. The OS can define the page table organization independently of the hardware. And it can also employ more sophisticated TLB replacement policies. The downside is performance overhead. You need to generate an exception, and you need to flush the pipeline execute the exception handler, and extra instructions are brought into the cache. Of course, you could handle this in another thread. So you may actually eliminate some of the performance overhead like the pipeline flush, but still there's overhead in executing other instructions to actually handle the software managed TLB. In hardware, if you handle it, you can have a specialized structure completely, as we will see in Intel systems soon. Okay, the final issue that I'm going to briefly touch on is when do we do the address translation in relation to cache access? And this becomes important, especially from the perspective of the L1 cache. Because at the if you need to do the translation to access the cache, now translation is on your critical path, right? Critical path of cache access. So this is a teaser. When do we do the address translation? Do you do it before or after accessing the L1 cache? And in other words, is the cache virtually addressed or physically addressed? And this is a fundamental choice at the L1 level, but you could also potentially move it to the L2, L3 levels, but it doesn't make sense fully at some point. And then the difficult question is, what are the issues with a virtually addressed cache? And there are issues. And one issue is synonym problem. Basically, two different virtual addresses from the same process or different processes can map to the same physical address, which means that same physical address can be present in multiple locations in the cache if you're actually using virtual addresses to address the cache. And this can lead to inconsistency in data because the same physical address in different multiple locations, let's say different sets, different indices in the cache. And if one of them is updated, the other one needs to be updated also or invalidated. So you have a coherence or consistency problem inside your own cache if your cache is virtual, because two different virtual addresses can map to the same physical address. There are other problems, actually. This is one problem. There's also a homonym problem, which is the fact that same virtual address can map to two different physical addresses. Why does this happen? Because virtual address can be in different processes, right? The same different processes have the same have the virtual address space to each of them, and the same virtual address can be mapped to different physical addresses. And this becomes a problem when you're managing the cache if it's completely virtual. So usually the solution to fix the homonym problem is to introduce address space IDs to distinguish between different processes and address spaces. This is easier to solve at hardware cost. Synonym problem is different virtual addresses can map to the same physical address. And again, why? Different pages can share the same physical frame within or across processes, right? Essentially, different virtual addresses can map to the same physical address. Just like we saw in the Google example, right? Different virtual addresses map to the same file, which is mapped to the physical memory. And many different virtual addresses can map to the same physical address. And there could be many reasons. Shared libraries, shared data, copy and write pages within the same process, files that are mapped. That's part of shared data, actually. And then the question is, do homonyms and synonyms create problems when we have a cache? And is the cache virtually or physically addressed? Becomes a very relevant question over here. And there are ways of solving the synonym problems also. I'm not going to go into detail. I have some backup slides for this, but I would like you to think about it if you're interested in this. So there are three ways of designing the first level cache. It could be physical, meaning it can the access of the cache happens after the virtual to physical address translation. You don't have the homonym and synonym problems, but you have a huge latency overhead. You need to access the cache, you need to go through TLB. And we discussed that first level cache is very latency sensitive. So you don't want to do that. In general, this is not done. The second option is you access the cache completely with virtual address and then do the translation. This is completely virtual, so there's too much flexibility and there's too many homonym and synonym problems because of this. As a result, this is also not done in general. Usually you do a compromise that looks like this, a virtual physical cache or virtually indexed, physically tagged cache, where you access the cache concurrently with the TLB, and then you do the tag check using the physical address. Now, for this to work, you need to design your cache carefully such that the indices, the virtual index, doesn't change during translation. So you should really not index the cache using part of the address that's going to change using the translation. Otherwise, you may actually map two different virtual addresses, two virtual addresses to two different virtual addresses that map to the same physical location to different locations in the cache. So if you didn't understand that, that's okay. But if you understood it, that's good, because that means that you've actually been really following what's going on in virtual memory. But think about what happens in this case. What kind of bits should you use for the index into the cache? And what can you do and what can you not do? So the idea is virtually index the cache, but do the tag comparison in the cache using physical addresses, because you will have the physical address at the end over here. Okay, and usually systems employ this sort of caches, virtually indexed physically tagged cache at the first level. The problem is not present in the lower level of the hierarchies because at that point you already have the physical address. You'd better do the TLB translation before the second level, for example. Okay, see backup slides for more. Let me now quickly go over a modern virtual memory system in Intel Skylake, and then we're going to transition to the epilogue part. So this is address translation has evolved a lot. So this is simple address translation in earlier systems. You have an L1 data, an L1 instruction TLB, L1 data cache, which is not part of your translation system, but usually you do it concurrently with the L1 data cache as we discussed. And then there's a software page table worker like MIPS. Modern address translation is much more complicated. Modern MMU, you can think of this as MMU. You have L1 and L2 ITLBs, L1 ITLB, L1 data TLB, L2 TLB, page table walker, hardware, page table walker cache to cache the middle levels of the page tables, multi-level page table. So there's a lot that goes on. And then there's also clearly the cache. So a memory management unit, we discussed it. It's the hardware that's responsible for resolving address translation requests. It's 1 MMU per core, usually. MMU has 3 key components, TLBs. We know what TLBs are. Page table walk caches. They essentially offer fast access to the intermediate levels of a multi-level page table. So TLBs cache PTEs, not the intermediate parts of the page tables, but page table walk caches cache intermediate mappings at the hierarchy, page table hierarchy. This is to aid the translation TLB misses essentially. And then hardware page table walker that sequentially does the page table walk that accesses the different levels of the page table to fetch the required PTE. And this is all in hardware. So now we can see that there's a big hardware over here. Okay, let's take a look at this MMU. Let's tear it apart in an Intel Skylake system, which is reasonably new. L1 data TLB, essentially, even this is complicated. Basically, they have 3 TLBs, each for different page sizes, 4 kilobyte, 2 megabyte, 1 gigabyte. And you can see the entries over here. There's only 4 entry 1 gigabyte TLB and fully associative. But this, you can address 4 gigabytes of memory with this. That's why it's 4 entry. 2 megabytes, 32 entries, you can address only 64 megabytes, right? With all of those. The 64 entries, you can address only 256 kilobytes, I guess, in this case. That's too bad. So this TLB is actually quite powerful. Even though it has fewer entries, it's very powerful because it really spans a 4 gigabyte portion of the physical memory. Okay, virtual memory, I should say, but also physical memory. I mean, if you think about it from that perspective, right? And virtual to physical mappings are inserted into the corresponding TLB after a TLB miss, clearly. And during a translation request, all 3 L1 TLBs are looked up in parallel. So now you can see that it's complicated. And having multiple page sizes clearly complicates the picture. And Intel folks did not design a single TLB with different page sizes because they thought it was easier to design 3 TLBs with different page sizes. And you can imagine, this is a cartoonish picture. You need to basically index these TLBs with different parts of the virtual address and do the tag match, etc. And then decide which one you hit on. Okay, so there's an L2 unified instruction and data TLB. Essentially, L2 unified TLB cache translation for both instruction and data. It's still private per individual core. And there are 2 separate L2 TLB structures now. One for 4 kilobyte and 2 megabyte pages, and one for 1 gigabyte pages. And you can see that these are bigger. But again, they decided to consolidate 4 kilobyte and 2 megabyte together. So the design of the TLB is a little bit more complicated for this one. Okay, but these are bigger, as you can see, and you can see the penalties. Of course, the question is, how can you support both 4 kilobyte and 2 megabyte pages using a single structure? There's not enough detail on this, but you can imagine, we discussed this actually when we talked about associativity in time. You basically index the TLB once using a 4 kilobyte index. And then if you miss, you index the TLB again. Okay, that's the idea basically. There are 2 steps basically. In time, you index the TLB assuming different page sizes. Okay. If you hit in the first step, that's good. Then it's a 4 kilobyte page. If you miss in the first step and in the second step, then it's a 2 megabyte page. If you miss in both, then you need to do the page table walk. The general algorithm is to recalculate the index and probe the TLB for all remaining page sizes. And we've seen this in associativity in time. If you remember the cache lectures, we said pseudo associativity. This is poor man's associative cache, if you will. We have associativity in space normally, but now we have associativity in time. We change the index and index into the cache again and again and again. And you can do it many, many times to get very high levels of associativity or support any number of page sizes. And this is the example basically. You first calculate the index for 4 kilobyte. If you miss, you calculate the index for 2 megabytes. Okay, so L2 TLB has n-step index recalculation. This is simple and practical. The downside is TLB hit latency is longer and varying. And now you have slower identification of L2 TLB miss, as you need to basically probe all page sizes. So potentially you can optimize it by making the lookup parallel. Of course, this adds hardware cost. Or you can predict the page size, predict the probing order. And trade-offs are, again, similar to associativity in time versus space. Okay, let's talk about the hardware page walker components. As we said, TLB misses are handled in hardware. And this is an interesting component, complicated component, that walks the multi-level page table to avoid expensive context switches and software handling of TLB misses. It has two components. One is a state machine that is designed to be aware of the architecture's page table structure, and then registers that keep track of outstanding TLB misses. So I'm not going to go into the details of it, but you can imagine how the state machine walks the page table. Of course, we actually saw the slide earlier. This avoids the need for a context switch on a TLB miss. It also has the ability to overlap TLB misses with useful computation, as we discussed. It supports concurrent TLB misses, because in hardware, you can support many concurrent misses. But of course, there's a downside: hardware area and power overheads. And now the software cannot change the page table organization and properties, if you will. It's etched into the hardware. Okay, so how do you do this walk? I'm not going to go through this in detail, but you start with CR3 register and then concatenate CR3 with the virtual address, and then you essentially do the walk of the multi-level page table that we discussed earlier. So it takes time, basically. Okay, but of course, there's benefit to it. That's why it's implemented in real processors. It allows overlapping of many TLB misses with useful computation. So if you do the software TLB mishandling, you need to context switch to a TLB mishandler, and then you do a load B. You cannot handle this TLB hit because you have a context switch, right? Hardware page table walk, TLB miss. Concurrently, you can handle other TLB hits, so you can do out of order execution, and you can get the full benefits of out of order execution, etc. Right? So you save a lot of cycles actually with hardware TLB mishandling. It's also called a page table walk, basically. Okay, finally, to aid this hardware page table walk, there are page walk caches. As we discussed, it's different from the TLBs because TLBs cache the page table entries, the leaf nodes in the last level page table. Page walk caches cache stuff, going back to this picture, from essentially all of these other levels, not the real page table that you're looking for. Why? Basically, you want to speed up the hardware page table walk. That's the idea. I already said all of this, actually. These are low latency caches that provide faster access to the page table levels so that the page table walker does not have to access memory or the cache hierarchy for every page table walk. It can just access these page walk caches, okay? And that's the Intel Skylake MMU for you, basically, in a nutshell, very quickly. And actually, there are other virtual memory designs. This is Apple A14 over here, based on some reverse engineering, etc. But you can see that L1 TLB and L2 TLB are larger in Apple A14, and also the page size, the default page size, is actually larger. I'm not going to go through the details of it, but you can enjoy the slide on your own. Okay, so we're at the end of virtual memory. So to summarize, virtual memory has a lot of benefits. It gives the illusion of infinite capacity. And we already discussed everything, so I'm not going to go through all of this again. This is a summary of everything we discussed. But it provides you the illusion of infinite capacity. It also provides you protection. That's very important. And there are a lot of issues that we need to solve along the way. And those issues all exist in real systems, and they're solved in some way. But there's more, which we're not going to talk about. How do you handle virtualized systems? Pose the problem. I'm going to flash a slide related to this. You may have virtual machines and hypervisors running programs, orchestrating systems. Now you have another virtualization layer. And that actually increases the number of virtual memory translations that you need to do. And existing systems provide support for that, called nested page walks, for example. I'm not going to talk about that, nested TLBs. There are alternative page table structures that we did not talk about. Inverted page tables, we briefly mentioned when you want to actually, the operating system may store the reverse mappings from physical pages to virtual pages to figure out what to replace. Some systems actually have inverted page tables to begin with, probably a bad idea, but there are trade-offs associated with it because inverted page tables are actually quite compact. In terms of storage size, these are small. Hashed page tables can enable fast access to the page tables. Actually, this may be a good idea to revisit in many systems, which we did not talk about. Basically, we just directly indexed. We didn't really do sophisticated hashing to the virtual address. And there's more that we don't have time to cover. But I will show you the one picture over here, which is the virtualized system. You may have a virtual machine, for example, like VMware. You may have a guest OS running on a host OS, running on the physical CPU. And this virtualized environment needs to have an additional level of address translation from the guest OS virtual address to the host OS virtual address. And then host OS virtual address needs to be translated to the host OS, the CPU physical address, essentially. And that requires another level of layer of translation, if you will. And this leads to a lot more memory accesses, basically. I'm not going to go over it, but it's a lot of memory accesses. And existing hardware, x86 hardware for sure, provides support for directly translating from the guest virtual address to the host physical address, while trying to avoid as much as possible this indirection level. So that's a direct support for virtualized systems. Okay, so let me conclude with this parting thoughts, the virtual memory part, and then we're going to have an epilogue for those who wish to stay in the rest of the lecture. But virtual memory is actually very important because it's one of the most successful examples of multiple things. Architectural support for programmers, how to partition work between hardware and software. So it's really hardware-software cooperation, which is similar to what I said over here. And it's a very successful example of the programmer-architect trade-off. It basically makes programmers' life super easy, architects' life, both system architect and micro-architects' life harder, as we have seen. But it is one of the most successful examples. But going forward, how does it scale into the future? It's not doing very well, in my opinion. And there are a lot of papers that are written on it. I'm going to show you some pictures of it also. But basically, we have increasing huge physical memory sizes, both local and remote. And 256 terabytes are starting to sound small for our memory sizes, basically, because data is huge. We have hybrid physical memory systems, DRAM, NVM, SSDs, and we want to increasingly manage everything using a single memory abstraction. There are many accelerators in the system addressing physical memory. They want to be part of the virtual memory. And there are virtualized systems, like I showed you earlier, hypervisors, software virtualization, local and remote memories. So how does it scale into the future? So the management is actually quite complex overall. So it's not going to scale very well. So there's one question. In case of hashing, will the synonym and homonym problems be reduced? Not necessarily. That's a very good question, but not necessarily. Basically, you still have a virtual address and you still have a physical address. It's just a way of determining the mapping. Okay, so if you want to learn more about rethinking virtual memory, we do a lot of that in my research group, actually. And this is one of the papers that we have written last year that rethinks virtual memory from different perspectives. You can also watch a lecture related to it. This tries to solve the rigid page table structure problems, translation overheads, which we have discussed many times, and heterogeneous memory management. But if you're interested, we're not going to cover it. You can take the future lectures or also read the paper. And there's a lot more in virtual memory. Like if you want to know more about the synonym and homonym problems, we cover that in other lectures, but we don't have time to cover it in this lecture. But you can also watch lectures. As you can see, there are multiple solutions to the problem. Okay, there are more lectures on virtual memory that I'm not going to go over right now. But hopefully this gave you a reasonably comprehensive overview of issues in virtual memory, which I think is critical to get exposed to as early as possible in your career, because it is a lot of cool ideas. It is a lot of complexity at the end, but it's one of those things that has been successful despite the complexity, heavy complexity, because it makes programmers' life easier.